Ladies and gentlemen, for this first one we have that the front view of a doghouse is made up of a square with an isosceles triangle on top. The doghouse is 1.35 meters high and 0.9 meters wide and sits on a square base. The top of the rectangular surfaces of the roof of the doghouse are to be painted. Find the area to be painted. Alright, super exciting stuff. See? So for these type of exercises that it seems like they do not give you a lot, you really need to focus on the buzzwords. Okay, these buzzwords are going to be hints for how to approach the problem, what information is missing, what that they can give you, etc. So let's read it again, thinking in buzzwords. The front view of a doghouse, okay, so front view makes reference to this guy here, ¿cierto? This is what I see on the front view of the doghouse, is made up of a square. Okay, so that tells me that this guy here is a square. Ta-da. With an isosceles triangle on top. So this guy here, see? All right, I'm going to stop right there. Let's apply what it just told us. So the fact that it's a square means that this side here, 0.9, makes this side here 0.9, makes this side here 0.9, makes this height here 0.9. Aha. And what does the fact that it's an isosceles triangle give me? It gives me that this angle is equal to this angle, and that this side is equal to this side. See? Let's remember that an isosceles triangle has two sides and two angles that are the same, while an equilateral triangle is one that has all of them the same. See? And your last type of triangle is a scalene triangle, which is just weird shit. Like all the angles are different, all the sides are different. It's, you know, it's a special boy. See? So just a quick recap. You have the isosceles, two of them are the same. The equilateral, they're all the same, all angles are the same. And then the scalene, which is, you know, whatever. Not even he knows what it is. All right, so those are the three types of triangle. Here we have an isosceles one. I already described it. I got all the info I could. So boom, boom, boom. Suddenly my diagram looks a lot nicer. See? You have to capitalize on the information that it gives you and work from there. So let me erase this real quick, make a little bit of space. Yeah. All right, we keep going. They tell us that the doghouse is 1.35 meters high, that is here, so I don't worry about that. 0.9 meters wide, that is here, and sits on a square base. All right, that it sort of tells me it's a square base just by giving me both of these 0.9s. See, you can assume that it's a square from there. But still, you want to double check that all the information they give you, you're taking out all you can out of it. See? All right. The top of the rectangular surfaces of the roof of the doghouse are to be painted. All right, that is another hint, actually. Because rectangular surface. So that tells me that, hey, what you're trying to paint, which is this guy right here, is a rectangle. Ah, interesting. And so what do I know about this rectangle? Well, I already know one thing. I know that this side here, 0.9, is also up here. I also have a 0.9 right there. Ah, so what is the height? Once I have the height, I'm going to have all dimensions of my rectangle, and I can find the area to be painted, right? And so this height is the same as this height here, see? Actually, the 0.9 is the same as this 0.9 over there. So what the hell is that height? Well, that height is the same height as my isosceles triangle slant height. So, let's figure out the dimensions of my isosceles triangle. So what do I know about this isosceles triangle? Well, I know that it looks like this, that this is equal to this, these are both h, and that here I have 0.9. All right, what else can I figure out about it? Well, if you're not sure, take a moment, look, reflect, think, but they do give me this height here, see? And the IB, something that's kind of cool about it, is that if they give you something, you probably have to use it. And so how can I use that height to find something about my isosceles triangle? Well, I have two heights that are sort of next to each other. I have this height here and this height here. So if I subtract both, I end up with only this, which is this height here. Ah, so I can do 1.35 minus 0.9. That gives me 0.45. The 0.45 is right there. 0.45. All right, and so how can I find the slant height from here? All right, so from here, there's actually a couple of options. I think my favorite is noticing that this triangle here is the same as this triangle here. So you can actually split them up. All right, let's look at the red one first. See, they're the same, but let's look at the red one over here. We have that this is h, that this is 0.45, and that here, ¿cierto?, is going to be this 0.9 divided by 2. 0.9 divided by 2 is 0.45. Okay, what else do I know? I know that this angle is equal to this angle, see, but I don't know what that is. All right, could help me in the future, who knows? But I do know that this is a right triangle. How do I know that for sure? Because I split my isosceles triangle in half. Okay, that is legal. So this is 90 degrees, 0.45. If you have a right triangle, you should immediately be thinking of the golden rule. Well, it's not called golden rule, but you have the Pythagoras theorem. Okay. All right, so you spot a right triangle, you think of Pythagoras theorem. See, what the hell is Pythagoras theorem? A squared, b squared, c squared. Okay. How do you know which one is c? A lot of people use this automatically, but they don't understand why. How do you know which one is c? C is going to be the hypotenuse. Okay, that's the fancy math word. If you want to learn it intuitively, which is how I like to teach it, it's the long one. Right? So the long one is going to be your c. All right, so the long one is here. A and B, you can switch them to place, doesn't matter. I'm going to call this A, I'm going to call this B, I'm going to call this C. All right, so 0.45, actually, there's probably more space up here. 0.45 squared plus 0.45 squared equals c squared. See? Let's remember that c is my h, ¿cierto? The same h that is in blue. Just so that we're on the same page, I'm just going to put h here. See? Yeah. All right, so I work it out, ¿cierto? Using my trusty rusty calculator. You will eventually end up with something that looks like this. Actually, no, I'll just show you. So if I use, to get h alone, see, what is next to it? It is a squared. See, what is the opposite of squared? Square root. So I do square root to both sides. And I end up with my answer. See? What does the square root actually do? It gets rid of this and this. I end up with just h. Alright, so h equals that. Got it? So I'm going to put that into my calculator. I'm going to go ahead and show you and everything. Give me 1 second while it loads up. Alright, so square root of 0.45 squared plus 0.45 squared gives me this. Alright, so this is my slant height. See? So h equals 0.636396. Alright, and that right there, okay, is the slant height. Is this h here. So now, the top of the rectangular surface of the roof of the doghouse are to be painted. Well, I know how my rectangle looks like now. See? This h here is going to be 0.636396. How do you find the area of a rectangle? Base times height. So I'm going to do this guy times this guy. So it's this guy times this guy. Boom. 0.5727. See? And so for this first one, you're going to write down, okay, the area of my rectangle is 0.5727. And I always like to put all the numbers because, you know, it's better. 56. See? You want to put your answer in the correct units. So you think of the units. We have meters, so we put meters. Now, if I tell you this is my answer, there are two things that are wrong here. Take a moment, think about it. One thing that is wrong is that my units have to be squared. Okay? Why? Because with units, squared is going to be area. Units cubed is going to be volume. Units to the power of 1 is just, which is the most common one, it's just going to be distance. Okay? So the power of 1 is here. ¿Cierto? That is to the power of 1, this is to the power of 1. Alright, we're on the same page. So that is one thing that is wrong. See? The other thing that is wrong is that here it says that the top of the rectangular surface is sides of the roof of the doghouse are to be painted. Do not forget that there is another rectangle on the other side. Okay, my art skills are not the best, but using a little bit of imagination, you know that there is a rectangle somewhere here. See? And so you need to find the area of this rectangle that goes like this, and this rectangle that goes on the other side. See? Actually, I'm gonna put it like that. See? So you have both of those rectangles, right? So I need to take this answer and multiply by 2. See? So I take this answer, I multiply by 2 because it is 2 rectangles. I'm basically adding twice, and that is my answer. So my answer is 1.14551 meters squared. Ladies and gentlemen, that is for the first one. Alright, so for the second one, we have that a vertical pole, okay, stands on horizontal ground. Okay, so that means that this is perfectly flat, this is perfectly flat. Awesome, beautiful. The bottom of the pole is taken as the origin. Oh, okay, so this is 0, 0, 0. And the pole has the coordinates this, which is this. All units are in meters. Okay, so meters is going to help for how I leave my answer. See, we can't forget that. Those are the units in this case. The pole is held in place by ropes attached at F, and one of the ropes is attached to the ground at a point A with the coordinates blah. See, coordinates blah are this blah here. The rope forms a straight line from A to F. So this is a straight line that is also going to be convenient. So for part A, we need to find the length of the rope connecting A to F. Now, before I jump into how to find the distance and all that good stuff, I'm sure a lot of you are like, dude, what the fuck? Why is there 3 numbers here? I'm used to numbers having just x, y. Well, surprise, you have x, y, z in this case. See? And so I know that that might look a little bit weird. Let me explain what is going on. So usually you have things that are like this. See, you have your x and your y. What is going to start happening now is that you are going to have your x, this is really hard to draw, your y, and your z. Okay, so it's something like a little bit 3D. See, so this x, y, you kind of like throw it flat on the ground here, ¿cierto? And you put z that goes straight up. See, so z is now your height, x and y are sort of like your horizontal stuffs, okay? So what is going on here is that your top of the pole, which is the point 0, 0, blah, blah, blah. So here we have f, see, which is 0, 0, 5.8. And your point A, which is 3.2, 4.50, is going to be somewhere here. So you're going to have, I don't know, 3.2 around here, 4.5 around there, and 0. See? So 0 means that it's at 0 height. That means it's a point somewhere around there. See? So that is my, what was it again? 3.2, 4.5, and 0. See? And so here I have a pole, ¿cierto? And I have a rope that goes like this. Okay. And so that is what's going on. And so when the IB says diagram not to scale, they are not joking. Okay, this diagram sucks. And when you see these 3 points here, you have to think, okay, I have something that's a little bit 3D. I have the thing that's up here. See, so drawing it, it's probably going to help you visualize the exercise a little bit. The point is you have this triangle that goes like this. See? And so what do I know about this triangle? What can I figure out? All that good stuff is our next approach. For part A, we need to find the length of the rope connecting A to F. Alright, so this is A, there is F, and you find the, that line, see the slanted one. So something that's convenient here is that because we're talking about a length, we are also talking about a distance, see? And so we are looking for the distance between 2 points. Alright, so if you think of length, the buzzword in this case, and you really think of distance, you should be pulling up your formula booklet and going, what the hell is distance? See? So here we have something from HL, we don't give a shit about that. Distance between 2 points, boom. Alright, that helps a little bit. But this is between 2 points, x1, y1, and x2, y2. In this case, I need z. So I keep looking, and boom, there it is. Here I have the distance between 2 points. when I have z in between. See? So that is the formula that we're going to be using for now. Look at that, how convenient how it shows up. There it is. I'm going to scroll up, make a little bit of space, and that is the formula we're going to use. See? So we have d equals square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Alright, so this is no different than the other distance formula, just that we have an additional point. So, yeah, I mean an additional thing, like z. See, z is now a thing. Alright, so what is z? What is z1? What is z2? What is y1? What is y2? All that good stuff. The only way you can mess up here is being unorganized, see? And so, dude, take your time, right? Like, don't make a small mistake that can be solved by something very easily. Write down both of your points. That is my first one. This is my second one, see? And then, using fancy colors, hopefully, write that this is your x1, this is your y1, this is your z1, this is your x2, this is your y2, this is your z2, see? I know this might seem like a little duh, but this way you also make sure that you don't mess up. See, so applying this to my formula up there, I'm going to end up with my distance being equal to square root of x1 we said 0 minus x2 3.2 squared plus y1, which we said was 0 minus y2 4.5 squared. Finally, plus z1, which is 5.8 minus 0 squared. See? All right, so this ends up being square root of negative 3.2 squared plus negative 4.5 squared plus 5.8 squared. See? All right, so put all of this into your calculator and you're going to end up with a distance of 8.00812. All right, this is my answer, but there's one thing wrong with it. Units. My units per meters. See? All right, so that is for part A. So the length of the rope connecting blah, blah, blah from A to F is 8.00812 meters. All right, then now for this next one, we have that we need to find FAO, the angle the rope makes with the ground. So they tell us that we need to find an angle in two ways. First, they say find the angle. Okay? The other way you can figure it out is because when they put it like this, FAO with the little hat, it's saying, hey, find this angle, A, in respects to the sides F and O. So this angle A in respects to the sides F and O. See? So that is the angle that we're trying to find. See? All right. So what do I know or what can I work with for finding that angle? So trigonometry should be coming to mind when we're working with angles. See? Now, when we think of trigonometry, there are three main tools that we have. See? We have sine, we have cosine, and we have the tangent. See? Now, sine, cosine, and tangent all have, sort of like nicknames. See? I'm sure you've heard that sine also has so, cosine also has so ka, and tangent also has so ka toa. See? Now, what the hell is this shit even saying, my guy? It's saying that for sine, you need OH. What is OH? It is opposite over hypotenuse. It's saying that for cosine, you need AH. AH is adjacent over hypotenuse. And OA is going to be opposite over adjacent. See? All right, so what do I have right now in respects to this angle that can help me figure it out? See? Right now, I only have one side. See, I have this side here, 8.00812. So, what side is that in respects to this angle? Well, looking at my triangle and how it looks like, it would be my hypotenuse. See? So right now I have a hypotenuse. That means I can probably use this one, probably use this other one, but this last one doesn't have hypotenuse, so boom. We're not going to work with tangent, not this time around. See? Now, I need either the opposite or the adjacent. See? All right, unfortunately, I don't have either. See? Opposite would be here, adjacent would be down there. See? So I need to either find one or the other and work from there. All right. Now it's your choice really which one you find and how you find it and all that good stuff. But for me, it's more intuitively to find all the adjacent, and I'll show you how and why. See? So I go back to my 3D, diagram thing, whatever, and I need to figure out one of the sides. See? So one thing that I can use immediately, see, is that this point A that I drew before has the x of 3.2 and the y of 4.5. All right, how does that help me? It helps me because right now I have two right triangles. I have one here and I have one here. And so with a little bit of creativity, what you can do is say, so this 4.5 is the same as this 4.5 over here. Boom! Suddenly, you have a right triangle that goes 3.2, 4.5, and what I'm gonna call, I don't know, whatever, F. Okay, F is gonna be this guy here. See? F, that I just called F. Actually, I should not call it F because F is the point up there. Fuck it, my guy. I'm gonna call this smiley face. So smiley face, okay, is the same as this point over there, which is the same as this side over here. Okay, so all of those are smiley face. See? So how can I find smiley face? Well, because I have a right triangle, see, you should immediately be thinking of the tools that you can use. You have trigonometry, but you also have the Pythagoras theorem. See, Pythagoras theorem says that a squared plus b squared equals c squared. Beautiful. And so the most important thing in the Pythagoras theorem is identifying, well, what is my c? And so c is always going to be your hypotenuse. See, that is a fancy math language. Hypotenuse is also going to be the long side. See, all of this are c. So the long side in this case is going to be smiley face. So I'm going to write 3.2 squared plus 4.5 squared equals smiley face squared. See? Okay, so I need to get smiley face alone, right? So I'm going to go ahead and do square root to both sides. What does the square root do? It helps me get rid of the squared. See? Boom. Now smiley face is alone. I just need to plug this into my calculator and see what I get. So I boot it up. I do square root of 3.2 plus 4.5. Oops, I made a mistake there. I need to make sure that they are all squared. So 3.2 squared plus 4.5 squared. All of this square rooted will give me smiley face. Smiley face is indeed 5.52. Let me write it out. 177. All right, so this is going to be smiley face. Okay? So smiley face is 5 points. I just want to make sure my diagram looks nice. 5.52, 177. All right, so we just found one other dimension of my triangle, one other side. See? So now we come back to this sine cosine thing, right? And so, do I use the one on top or the one on the bottom? Did I just find the opposite or did I just find the adjacent? Let's remember that the opposite to my angle is all the way on the other end. It's not something we have. Okay, so we're not going to use sine. In this case, the winner will be cosine. See, we're going to use adjacent over hypotenuse. The adjacent we identified is 5.52, and the hypotenuse is 8.008. Okay. All right. Remember that this adjacent hypotenuse thing is relative to the angle you're trying to find. See, this 5.52 was the hypotenuse when we were trying to find the side. See, here it was the hypotenuse for finding the side, but it's not the hypotenuse anymore in respects to this angle. See, and since we need to find angle FAO, we need to work in respects to that. Okay, so angle FAO is going to be cosine of FAO equals my adjacent, which we said was 5.52177, getting divided by my hypotenuse, which was 8.00, 812. All right, and a lot of people here are confused on what the hell to do next. See, why do they get confused? Because they're not sure how to get FAO alone. See, there's a cosine next to it. What the hell is going on? Like, what happens? See? Yeah, let me explain it this way. If you have 2x equals 6, and I say, all right, homie, what is the value of x? Well, 2 is multiplying x, ¿cierto? And so you divide by 2 because 2 is multiplying x. Why? Because division is the opposite of multiplication. Division is the opposite of multiplication, x is 3. See? All right, ladies and gentlemen, what is the opposite of cosine? The opposite of cosine is cosine inverse. So I do cosine inverse, and this is the main idea I wanted to share. Cosine inverse of cos, FAO stays inside, ¿cierto? And I still have my fraction on the other side. See? That is a decimal. There is a decimal there. Yeah. See? And so what does cosine inverse do? Well, it makes this guy, oops, I actually messed something up here. There's a cosine inverse here. What does cosine inverse do? It makes this guy and this guy go away, and I end up with only angle FAO being equal to cosine inverse of this whole thing. So what the cosine inverse does is that when it is next to a cosine, it deletes that cosine, see? And you end up with only what's inside, see? Notice that my angle FAO never left the scene. Whoops, that was an accident. But yes, cosine inverse does not affect what's inside, okay? FAO stayed there the whole time, see? So I'm going to pull up my calculator, do cosine inverse of this stuff, see? So I take this, I divide it by 8.00812, and I end up with angle FAO being equal to 46.40. We want to write it out, it's there, see? 7. All right, and so if we look at my answer key over here, just so that we're on the same page, that is the answer that you just got, see? So beautiful, there it is. I did want to show something on the answer key, which is relevant for any trigonometry problem, okay? In trigonometry problems, you usually end up doing weird divisions and end up with very long numbers, see? You need to plug in those long numbers into your calculator in order to get the exact answer, see? If I don't plug in the long numbers and say I would have done cosine inverse of, say, 5.52 divided by 8.008, so it's like not exactly the same number, my answer is a little bit different, okay? On sig figs, it's probably going to end up being the same. It doesn't matter, but I'm just pointing it out. If you're comparing your answers and it's a little bit different, it could be that you're doing that. See? It's just something common. I'd rather bring it up so that no one out there is confused. Ladies and gentlemen, that is for number 2.
Alright, and for this third one, we have that the height of a baseball after it is hit by a bat is modeled by the function blah, where h of t is the height in meters above the ground and t is the time in seconds. So h of t is height, okay, and t is time. And here we have our units. I'm going to put them in red. We have meters, we have seconds. Alright, so for part A, we need to write down the height of the ball above the ground at the instant it is hit by the bat. So take a second and think about it. So first things first, we have our function. See, our function is h of t equals negative 4.8 t squared plus 21t plus 1.2. So a couple of things, a couple of common misconceptions. First of all, h of t, which is practically the same as f of x, is the same as y. Okay, so if for you it's easier to think of this as y equals, then by all means do so. This is y, this is technically x, and this is also technically x. All right, so that's the first thing. If you'd rather think about it that way, go ahead. All right, I'm just going to do it the original way because, you know, whatever, I'll be consistent. But just to clear up some doubts that people might have, that's the first thing I'm going to say. The second thing I'm going to say is that context matters for these kind of questions. So if we need to write down the height of the ball above the ground at the instant it is hit by the bat, you need to think, when is it hit by the bat? When is it hit by the bat? Well, t is time, right? And t is time in seconds after the ball was hit. After the ball was hit. So in 0 seconds, the ball is getting hit. In 0 seconds, the ball is getting hit. In 0 seconds, the ball is getting hit. So we plug in 0 for t. We have 4.8 parentheses 0 squared plus 21 parentheses 0 plus 1.2. We do all of this in our calculator. You end up with t equals 1.2. Why does this happen? Well, negative 4.8 times 0 goes away to 0. Anything times 0 is 0. 21 times 0 goes away to 0. We end up with just this guy. See, so t is 1.2. Now, what set of points is it? Well, since I plugged in 0 here, that means I have 0 comma something. What is my something in this case? What I got over here, 0 comma 1.2. So if I go ahead and graph this, there's a couple things I know about it. First of all, I'm going to have the y-axis over here at 0 comma 1.2. And I also know that it is a parabola because of the squared. So it's going to be something like this or like this. Which of the two is it? It is the one on the left because there is a negative sign. If there's a negative sign, it looks like this. If there's a positive sign, it looks like this. What's a way to remember it? If it's positive, it's happy. This looks a little bit like a smiley face. Might look a little bit creepy, but there it is. Anyways, so my graph looks probably something like this. All right? Whatever. That is part A. Part B. Find the value of t when the ball hits the ground. So, when it hits the ground, am I talking about my y or my x? In this context, I would be talking about my y. Why would it be my y? Why would it be my y? Because y is height. Okay, so when the ball hits the ground, ground is going to be a sort of height, and the ground will be height of 0. So how do I express height of 0? I express height of 0 by saying y equals 0. How do I say y equals 0 in this context? By making this equal to 0. So I make h of t equal to 0. Notice that there's a difference between h of t being equal to 0 and h of 0 being equal to something. Okay? In the first case, you are making your y equals 0. In the second case, you're making your x equals 0. All right, so really let that sink in. Okay, that is very important. Anyways, in this scenario, we're doing the case on top. So my y is going to be 0. See? So I'm going to take my trusty rusty, formula thing imaging over here. I'm just going to make some space. Give me a second. Okie dokie. So again, we're making y equal to 0. Why are we making y equal to 0? Because we're analyzing when the ball hits the ground. See? My y is height. That's why I work it that way. So all of this has to be equal to 0. See? So 0 equals negative 4.8 t squared plus 21t plus 1.2. And when you're in this scenario with a parabola, okay, you have a couple options to find it. See? You have 3 main options, all right? And I hope some of these ring a bell. So you have factoring. You have just straight up the quadratic formula, see, which looks like this, negative b plus or minus square root b squared minus 4ac divided by 2a. Okay, this thing that you've probably seen before, this gives you the zeros, okay? And the last option is just calculator stuffs, see? I'm going to choose calculator stuffs because even though it might be a little bit slower sometimes, it always works, see? And I'm all for following a process that you can always do. And so that is what we're about to do. So, how does it work? Well, first things first, we're going to plug in our equation up here. See? So I'm going to put negative 4.8 x, in this case t, but in my calculator can only put x, squared plus 21x plus 1.2. I go ahead and graph. All right, so I got a little bit lucky. I can see part of my graph. Now I'm going to play around with my window. See? Now, before playing around with my window, I got to understand I need to be able to see the zeros on my graph. What do I mean by zeros? I need to be able to see this guy and this guy. See? I need to see the zeros of my x-axis. So where my parabola cuts through the x-axis. Why is it called zero? Because both of these points, okay, both of these points are x comma something. Oh, fuck. I said that very incorrectly. Both of these points are x comma 0. Okay, and so that's why they're called your zeros. See? So it's something comma 0. All right, it's something comma 0. And so using my calculator, I'm going to go ahead and try using zoom standard, which is zoom 0. Okay, sorry, zoom fit. So zoom and 0. Press enter. I see if I get my zeros, and I can see that I get one of them. See? I do not get the other one though. Now, let's take a moment. Here I am seeing one of my zeros, right? I'm not seeing the other one. The other one is on the left side, which is actually conveniently how I drew it here. Do I care about the one on the left? Do I care about the one on the left? Well, x is, what was x again? X was time, see? Time in seconds. What was y? What was height? Height in meters. So anything to the left of here, see, so I'm going to put it in this sort of yellow. Anything to the left is going to be a negative value. Now, ladies and gentlemen, does a negative value make sense for time? Can you have negative seconds, negative minutes? Well, it depends how high you are. But hopefully you're not high in math class, okay? This negative value, this 0, is not a valid solution because of the context, okay? It exists in my parabola, but given the context of a of a ball getting hit by a bat and when it lands and etc. and blah, 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 and time being in between, negative time makes no sense. So it is okay that my calculator shows the 0 on the right side because I do not give a fuck about the 0 on the right side. Why do I not? Because of the context. I only care about time values that actually make sense. So, whoops, I forgot to show a little bit. So, procedure. You put your formula in y equals, see? Then you will be calculating. See, you're calculating your zeros. Where is calculate? Second trace. See? So that blue button up there, you might want to hit calc. Okay. So, of course, now I'm looking at my zeros. Now you know why it's called a 0. Why was it called a 0? Because your x-intercepts are x comma 0. See, it's something comma 0. That is why they're called zeros. Yeah, but so we pick 0. It is asking for left bound and right bound. What is that truly asking for? So, this is what your calculator does. You have your function, it looks like this. You have two zeros that I'm going to put in red or orange. You have this one and this one. So when you have left bound and right bound, you are restricting the area that like your calculator scans, and that way you make sure you get the 0 that you want. If I want the 0 on the right side, it would be wise to put a left bound here, a right bound here, and that means my calculator will scan like this. It'll find all the zeros in there, which of course is only one. So left bound, right bound does matter. I imagine you can already tell that if your thing is like this, and your left bound, right bound is something like that, you're going to have trouble because there's two of them. See? So left bound, right bound does matter, and that is why. See? All right, so I'm going to put left bound over here, right bound over there. Should be good enough. Now they give us guess, okay? Okay, your calculator knows where the 0 is. Guess is really like pick the 0. See? You're like mega double checking, all right? Which is actually convenient in a case like this one. But anyways, I'd much rather care about you understanding why you're picking a left bound, why you're picking a right bound. As long as you understand the why in things in life, you can like really dig deeper and get to know stuff better. See? Don't get used to memorizing stuff. Understand why. This is what your calculator is doing. Left bound, right bound. Which flipping 0 are you asking for? There it is. My 0 is 4.431415. So I'm going to write that over here. So for part B, we have that it is 4.431415. Do not forget your units, seconds. And if you would like to do three significant figures, it would be 4.43. Why is that three significant figures? Because you go 1, 2, 3. On the third one, you compare it to the one on the right. Do you round it up, or does it stay the same? It stays the same because this is a 1. And yeah, that's about it. Three significant figures is the one on the bottom. Up top is the long version. I recommend the long version always because then you know, don't mess up the significant figures because it can happen. All right, whatever. Now the last part, which we actually talked about a little bit earlier, we have part C. So for part C, we need to state an appropriate domain for T in this model. Now I'm sure some of you are already thinking, what the fuck? What the heck is domain? Yeah. Intuitively, I'm not gonna, there's more space up here, so I'll do it up here. Intuitively, when we talk about domain, it's going to be your x values. When we talk about range, okay, that will be your y values. And so part C is asking for state an appropriate domain for T in this model. So it says for T, which is like a hint, like, hey, it's about your x values, see? So for T. I actually touched upon this earlier, right? So if I have time for my x, cierto, for my domain, all right? For my x-axis and my y-axis is height, it makes sense that my domain has to be positive. See, I cannot have negative time. I can only have positive time. So initially, I would say, well, time has to be from 0 to infinity. See, that would be my first initial thought. However, and this is where the IB gets a little tricky, okay? However, if you go from 0 to infinity, how does my model look like? Well, my model would go from, and when we talk about model, we're talking about like basically just your function, okay? Your function given the domain you're, you know, choosing. So my function would look something like this. It would go until there. And so choosing a domain from 0 to infinity leaves all this extra space, all this extra data that I don't really care about. See? You don't really care about, you know, the ball going into deep underground in the center of the earth because that's just not realistic. It's not what you care about. See? So all of this data here, you don't really give a crap about, okay? And so that's when you start thinking, okay, maybe my domain should be a little bit smaller. Okay, how smaller? Well, when does it touch the ground? When did it touch the ground from part B? It touched it at 4.43 seconds. Ah, so a wise domain is what I have in orange here, which from 0 to 4.43. Okay? How do you write that in fancy math language? You can say that your t has to be greater than 0, see, which is doing this. Um, and also t has to be less than 4.43, which is you doing this. Okay? What do you end up with? You end up with what's in the middle. See? All right, cool. What's another fancy math language that you can use? You can go like this. All right, that expresses the same thing as up top. They are synonyms. And believe it or not, you can also just say t has to be greater than or equal to 4 blah, blah, or sorry, or equal to 0 and less than or equal to 4.43. And so these three ways that I just wrote it out are all super valid. They will all score the maximum amount of points. And that would be part C. Before we move on to the next problem, all right, a quick sort of hint that applies for everything. See? Notice, for part C, we needed to state an appropriate domain for T in this model. And what we defined was that our appropriate domain for T in this model is when the ball hits the ground. See? After the ball hits the ground, we don't care about that data. See? We don't care about the data that goes after this, right? We don't give a crap about that. We only care about our data when the ball it gets hit and then when the ball hits the ground. Now, how did I figure out that this was 4.43? Well, it was from part B. See? So the sort of hint or the sort of idea that I want you to start getting in your head, all right, is that what you do from part A can help you with part B, and what you do from part B can help you with part C. All right, that can be a helpful thing for if you're stuck in part C or you're stuck in part B. Think about it. Yo, what did I do last? Does that help me with what's coming? Sometimes it doesn't. I mean, what we did in part A wasn't really necessary for part B, but what we did in part C was essential for part B. So take a moment, think about it. All right, that kind of stuff matters. It adds on, and at the day of the test, it's a tool you might need. That is for the third one. All right, for this next one, number 4, we have that 3 towns, A, B, and C, are represented as coordinates on a map where x and y axis represent the distances east and north of an origin. Okay, that is why we have this north symbol over here, and technically we should have an east symbol over there. Okay, so that would be my x, that would be my y. That is what it's telling me. Blah blah blah. Our units are kilometers. Units are important. We're gonna leave that highlighted. Town A is located at negative 6,1. That is this here. Town B is located at 8,6. That is this here. And we have a road that runs along the perpendicular bisector of AB. This information is shown in the following diagram. Perfect. All right, so before we jump into part A and part B, what the fuck is a perpendicular bisector? All right, so let's start with a couple, a couple hints. See? First things first, the word perpendicular should be ringing a bell, okay? You have two types of lines, all right? You're going to have parallel, you're going to have perpendicular. I mean, these are the type of lines we should like really care about, okay? So perpendicular, or actually no, let's go with parallel first because I think it's a little more friendly. So parallel lines look something like this. Okay, what is cool about parallel lines? Not that you have to be a nerd to find it cool, but what is cool about parallel lines? That they have the same something. They have the same slope. So parallel lines have the same slope. All right, a perpendicular line, which I'm going to draw down here in red, looks something like this. Okay, clearly the slope isn't the same there. Also, perpendicular can look like that. All right, so don't flip out if you ever encounter something like that. The thing about perpendicular lines is that they have like, it's not really an inverted slope. It's a reciprocal slope. I'm going to explain reciprocal in a second, okay? And so parallel lines have the same slope, so they never touch. You can describe it like this. And perpendicular lines make 90-degree angles where they intersect, okay? So that's just a couple more nerd comments coming your way. A reciprocal slope looks like this. If, let's say, this line here, okay, has an angle of, a slope of, say, 1/2, that means that the perpendicular line to that, okay, its slope is going to be -2. That is reciprocal. Okay, how did I reach -2? So I take 1/2, I do the reciprocal of it. Okay, so first of all, I first flip it, and then you multiply by a negative. So I flip it, so it's 2/1, and then I do the negative, -2/1, which is just -2. Okay, let's make one more example. So for the reciprocal, you sort of flip it and then times it by a -1. Let's say one of my slopes is -3/4, and I tell you this is the angle of line 1, line 2 is perpendicular to it. What is the slope? Well, first you flip it, ¿cierto? First I flip it, so it's going to be -4/3, and then I do the negative, see? Then I do the negative, I end up with 4/3, see? Because negative times negative gives me positive. Okay, so that's just a little bit of an idea for what the heck reciprocal slope is, see? if you want to get really fancy about it, if you know that you have perpendicular lines, then what you can do is say that your first slope times your second slope will always have to equal -1. See? So if you want to remember like a more mathy way to go about it, it's this. Intuitively, it's this. Okay? Cool. So keeping that in mind, that is what perpendicular is about. Now, what the hell is bisector? Okay, so bisector, following its name with bi, we're talking about two, ¿cierto? All right, so, and sector, and this sounds a little bit like the word dissect, okay? So when you dissect something, you're opening it up, stuff like that, etc. If you bisect something, you are cutting it in half. Ooh, what did I say? Cutting it in half. What is that telling me? So this road, C, okay? I mean, no, not C, sorry. So this road, okay, is this guy here. And so what that road is doing is that is the perpendicular bisector of AB. AB, I'm going to put in pink. Okay, so AB goes like that. Now, since the road is the perpendicular bisector, that means that, first of all, the slope of this is going to be the reciprocal of this one, okay? And second of all, since it's the perpendicular bisector, that means that this distance is equal to this distance. So if this distance is 3, that means this distance is 3. Okay, so there's two things going on. That it? And after this, we will jump into part A and part B. I just think it's important to leave all of this defined first, okay? Perpendicular bisector shows up quite a bit, and those words scare a lot of people. That it? So on one side, we have the perpendicular thing, which makes you flip slopes and put a negative on it. And on the other side, we have the bisector, which gives us the information that this half is equal to this half in terms of distance. All right? Cool. So now that we understand the vocabulary and what's going on and all that good stuff, let's jump into it. Part A. Find the equation of the line that the road follows. All right, cool. So since we know that it's a perpendicular bisector, we need to capitalize on that information. See? So what I can do for now is get the slope of the guy in pink. Okay? So the guy in pink, how can I work around it? Well, the slope formula, which is in your formula booklet, is over here. So I'm going to go ahead. Oh, slope doesn't show up. Gradient maybe? Gradient. Okay, so, I'm glad that happened so I can show you something. Gradient is the same shit as slope. Okay, they are synonyms. So gradient equals slope. This is my gradient or slope formula. I'm going to write it down over here. See? It is m equals y2 minus y1 divided by x2 minus x1. Now, some of you have probably heard, I know that slope is rise over run. See? This is a very common way to teach it. It's rise over run, and everyone memorizes it this way. And they do like this thing, and then they count this way, and then that's rise over run. Okay, sure. Correct. Whatever floats your boat. Notice the following. This y, if we think of an axis, ¿cierto? This y is up here. And y is for vertical. See? Y is my vertical line. And so it makes sense that anything rising has to do with my y values. See? So that is why my y values are on top. The rise is just going to be y2 minus y1. See? The run is just going to be x2 minus x1. See? Because my x is going to be my horizontal, or where it's going to be running. See? And here's my rise. And so they're just a little bit of a intuition sort of thing. If you ever forget the slope formula, but you remember the rise over run, you can recall that, okay, so if it's rise over run, my y values have to be on top. Therefore, my x values are on the bottom. See? So they're just a little bit of intuition why that formula is the way that it is. Let's move on. All right, so I have my slope, see? Or let's say I have my slope formula. y2 minus y1 divided by x2 minus x1. And I have my 2 points, see? I'm talking about the ones in pink. And so a lot of people here can kind of get tripped up on like, what is my x2, what is my x1, how do I define that, blah, blah, blah. Right now I have 2 points. All right, so now let's go ahead and define which are my 2 points that I have. So on one side I have point A. Actually, I'm going to do it down here. So on one side I have my point A, which is -6, comma, -1. And on the other side I have my point B, which is 8, comma, 6. All right, so a common mistake that people do here is that they get mixed up on what is x1, what is x2, what is y1, what is y2. And so x1, y1, x2, y2, x3, y3, all make reference to a set of points. Okay, so you always have sets of points here, see? And you need to be consistent. So x1 has to go with y1, x2 has to go with y2, x3 has to go with y3. You cannot have a point that is x1, y2. Okay, that is illegal. That we do not do that. Okay, that is illegal. These two are correct. These three are correct. Why is this one illegal? Because this one does not go in line with this two. Okay, so you really gotta be careful, and I strongly suggest you write out your points and are just very, slow about it. See, there's no reason to make a mistake here. Just take your time, write down the points, which is what I just did with A and B, and define x1, define x2, define y1, define y2. So I'm gonna do that now. X1 is gonna be -6. Y1 is gonna be -1. X2 is gonna be 8. Y2 is gonna be 6. Okay, that's a small step, but it can actually get you very far. So y2 is 6, minus y1 is -1. Whenever I plug in a negative, I strongly suggest you put it in parentheses. Okay, just a rule of thumb. That way it's less likely that you mess up a double negative. On the bottom, I have x2, which is 8, minus x1, which is -6. So I do plug in parentheses again. So up top, I have double negative. That makes 6 plus 1. If you ever have trouble remembering that double negatives make a positive, okay, here is a trick that I like to use. So we're going to say that we're going to say that, we're going to say that negative is going to be, hate, all right? And we're going to say that positive is going to be love. And so, if I have, let me just copy this real quick. If I have a negative and then a positive, see? And I read it out loud, this says, if I hate to love, I'm a hater. So it's negative. If I love to hate, what am I? A hater or a lover? If I love to hate, I am a hater. If I love to love, am I a hater or a lover? I'm a lover. And if I hate to hate, then that makes me if I hate to hate, I'm a lover. See? All right, whatever. Here's a little bit of a pattern to remember the negatives and positives and whatever. I just mentioned it because I know some people have trouble with it. Might as well put it out there, see? So up top, it's double negative. You hate to hate, you're a lover. On the bottom, we have the same thing, double negative. You hate to hate, you're a lover. So it's going to be 6 plus 1 divided by 8 plus 6. What does that give me? It gives me 7 over 14. I can simplify this a little bit. I end up with 1/2. All right, so what is this 1/2? Why were we doing this? We were doing this for the gradient formula. Okay, and that gave me the slope. It gave me the slope of what? It gave me the slope of AB. So M1 is going to be M1 is going to be 1/2. All right. I'm just going to call this my line 1. Okay, the thing in pink is going to be line 1. That is my slope. See? So what does that tell me about line 2, which is going to be in blue? Okay, what does that tell me about line 2? The road. See, road is going to be L2. What does that tell me about the slope of L2? Well, L2 is the perpendicular bisector to L1. So the perpendicular part tells me that I need to flip it and do a negative. See? So M2 is going to be my slope of L1 flipped and then, multiplied by a negative. See? So first I'm going to flip it and then I will do the -1. That means my slope is -2. So M2 is -2. All right. So for the equation of the line that the road follows, which is for L2, I already have the slope. See? Um. All right. There's a couple of ways for finding how do I say it? The equation of a line. See? The one that I think is the best, which I think is in your formula booklet. Do I have what I need? Distance. Sorry, give me 1 second. Whoops, not my Instagram. Ah, it was in front of me the whole time. Okay, so I am trying to find the equation of a straight line. See? Which is exactly right here. And so I have three options. I can either use this guy in the middle, or this guy on the right side. See? All right, there's a couple of things going on with each. The one that I almost always use for finding a new equation, see, so I strongly suggest you stick to this, is this guy here. All right, this guy is called the point slope formula. All you need to make it work is two things. You need the slope and you need a set of points. So if you have the slope and a set of points, you're good to go. See? So coming back to what I have over here, I do have the slope. See? Awesome. Do I have the set of points? Not yet. How can I get it? All right, so I know that this road cuts through the pink line. See? So I know that this point here is in both equations. All right, so now that I'm trying to find this point here, see? I need to use all the information I can. So first of all, it goes through both lines. It goes through L1 and L2. See? The other thing I know is that L2 is a perpendicular bisector to L1. So remembering the bisector thing, it is cutting it in half. See, so the distance here is equal to the distance here. All right, so that is actually a bigger hint than what we think. Because what I can do is that I can look at my change in X and my change in Y, find halfway through both, and I'm good to go. What do I mean by this? If I were to put this on a grid line, okay, and make it a little more pretty. All right, so I know that I'm first going to put point A. All right, so I know that point A is 1, 2, 3, 4, 5, 6, -6, comma, -1. See, so this is point A. On another side, I have point B, which is at 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. It's going to be around here. All right. Point B. Okay, I know it's not drawn to scale. I know it's not pretty, but it will make a very good illustration of my point. And so what is the halfway from A to B for my X values? For my X values. So if I'm only comparing my X values, and here I have -6 for my X values, and here I have +8, 6. So if I analyze only my X values, I'm going to be taking this guy here and this guy here. So if I make a number line and I put this -6 here and this 8 way over there, and I put everything in between, I'm going to see that I have -5, -4, -3, -2, -1, 0. Okay, so here I'm going to put 0. 1, 2, 3, 4, 5, 6, 7, 8. See? And so if I ask you to find the halfway point now, it's going to be so much easier. See? And so what I like to do is that I jump once here, I jump once there. I jump once here, I jump once there. So over on this left side, I am now on -5, -4, -3. Over here, I am on 7, 6, 5. See? -2, 4, -1, 3, 0, 1. And now if I were to do this like one more time, they will both meet over here at 1. So what does that tell me? That my middle point for my x values is going to be 1. So this point here, I know has an x value of 1. 1 comma something, see? For the other one, we can do the same thing, see? So we're going to go ahead and do a number line comparing -1 and 6. So go ahead and do a number line. Here I have -1. Here I have +6, see? I'm going to do this one a little more detailed because I think the last example maybe wasn't so clear. This is going to be 0. This is going to be 1. This is going to be 2, 3, 4, 5, and 6. So what is the middle point? Well, I'm going to jump once here, jump once there. Jump once here, jump once there. Jump once here, jump once there. And so now, since it's, they're like facing each other, that means that my middle point is actually going to be right here. So that is my middle point, see? If they both jump one more time to meet in the middle, it would be 2.5. All right, anyways, there's a lot of different ways to do this. I think the number line thing is super useful. You can also do the number line thinking about it like this, see? So you could count this way. So here it would be for my x values. And you can also jump for your y values like this, see? Jump like that, compare with this, see? Again, there's a lot of different ways. I'm just showing the one that I think is the most intuitive, to each their own. Got it? So here it's going to be 2.5. Over here we said it was 1. So that means my x value is 1. My y value is 2.5. All right, so now I have the slope and the set of points. That means I can apply the point slope formula, which looked like this. See, we had y minus y1 equals mx minus x1. All right, so what is my y1? 2.5. What is my m? -2, ¿cierto? -2 from before. X minus x1, which we said was 1. See, this one here. All right, cool. So if I go ahead and solve this, then -2.5 stays on the left. This -2 is going to distribute, so I'm going to end up with -2x plus 2. I throw the 2.5 on the other side. I end up with y equals -2x plus 4.5. All right, and that is pretty much for part A. That would be part A. Later on for part B, they tell us that town C is due north of town A and passes through town C. Find the y coordinate of town C. And so what we need to identify here, see, is what we know about point C. So we know that point C cuts through L2, okay? So that means I can use this guy here. Okay, that is my L2. It's what I found in part A. Got it? So I can use that guy there, see? And what else do we know about point C is that it is due north of town A. Now this detail here, although it seems small, is super important. Okay, because it is due north of town A, you can assume it is due exactly north of town A. What does that mean? Since it is due only north, that means my east or west remains unchanged. And so what is my east or west of point A? It is -6. So I know that point C is -6, comma something. Once I find that something, I will have all of part B. All right, cool. So I'm gonna go ahead and plug in -6. I'm kind of running out of space, but I think I can do it up here. See? So I'm gonna plug in -6 into this equation. I end up with y equals -2. Whoops, sorry. Y equals -2 times -6 plus 4.5. So y equals 12 plus 4.5. Y equals 16.5. So that means that my point C is going to be -6, comma, that is a 6, -6, comma, 16.5. So that would be my point C. That would be for part B. And that is number 4. I think it's important to highlight 2 things here. First of all, fucking perpendicular bisector. I know it's weird, but it's more intuitive than what you think, okay? The perpendicular part makes reference to slope, okay? And the bisector part makes reference to a same distance cutting in half, see? The other thing that's important to point out is that part B needed part A, all right? And that is a pattern you can notice in a lot of IB questions, not just in math. Part B, you needed something from part A. Okay, so if you were in part B and you were thinking, damn, I don't know what the fuck to do, think about what you did in part A. It just might help you, and in this case, it was key. Because for part B, we needed the equation we found in part A. Consider that, and yeah, that is number 4. Alright, now for number 5, we have that the ticket prices for a concert are showing in the following table. Here is the table. Okay, so they tell us that the ticket type for adult has this price, for children has this price, for student has this price. Then they tell us three pieces of information: the total amount of tickets, the total amount of money. So we have total tickets, total money, and also that lastly there were twice as many adult tickets sold as child tickets. They tell us that we need to let the number of adult tickets sold be X, the number of child tickets sold be Y, and the number of student tickets sold to be Z. For part A, we need to write down 3 equations that express the information given. And for part B, find the number of each type of ticket sold. Alright, so I'm sure some of you are like, dude, what the fuck is going on? Alright, check it. So this right here, the big challenge, okay, is identifying what equations you can do. See? And so you will quickly realize this has to do with a system of equations. Okay, what am I talking about when I say a system of equations? Let's say you have, I don't know, x plus y equals 2, and then on another side you have whatever, uh, 3x plus 2y equals 9. I'm just making this up, okay? And you have the system of equations. And I tell you find the values of x and y. Okay, first of all, you can find them because your number of variables is equal to your number of equations. See? So you have 2 equations, but 2 variables, okay? You're good to go. And so here, and this might start ringing a bell now, you have substitution or elimination, okay? If you're not sure what that is, don't worry, I'm about to show you, okay? But this is sort of like the world we're in right now, just so that we get situated on what's going on. The big challenge here for these type of word problems, I think, is defining well what type of equation you can get, okay? And so forget for a second like where x should go, where y should go, and like what number should be next to it and all that shit. No, come on. Think a little bit more about the context, okay? So what information do I have? On one side, I have information regarding price, see? And so this guy, I mean, this whole table is price, ¿cierto? And here I can make an equation based on this for, yeah, it would be like price or like earnings. See, price and earnings would be the one in the middle. The one up top has strictly to do with amount, okay? It has nothing to do with price. And the one on the bottom also has to do a little bit with amount, okay? And so if you start thinking about it that way, you can have like a better sort of approach to what is going on. Okay, so this isn't random information. The first one has to do only with amount, nothing with price. The second one has everything to do with price and amount. And the last one has only to do with amount. My variables, what are my variables? My variables, are they in price? Are they in amount? What's going on? This is all number of tickets sold. Number of tickets sold. Number of tickets sold. So this is also all in amount. Okay? So X, Y, and Z is an amount. It is not a price. All right, now we're getting somewhere. So for this first equation, okay, for this first equation, using this information here, total of 600 tickets were sold. Since X, Y, and Z are all amount of tickets, that means that all my adult tickets plus all my child tickets plus all my student tickets has to equal 600. Okay, now we're getting somewhere, right? What else can we do? Well, for this second one, we have that the total amount of money from ticket sales was 7,816. So a lot of people, what they do here, which is a common mistake, which is I'm about to show you, is that they say, okay, X plus Y plus Z has to equal 7,816. Okay, why is that a mistake? Take a second, think about it. It's a mistake because X, Y, and Z are an amount. See? And so, since this is earnings of the ticket sales, right? So it's all your adult tickets that were sold plus all your child tickets, how much they earned, plus all your student tickets and how much they earned. So, my question to you, ladies and gentlemen, is what is the price of an adult ticket? Aha. The price of an adult ticket is 15. So we have 15x. What is the price of a child ticket? Aha, 10. 10y. What is the price of a student ticket? 12. 12z. So 15x plus 10y plus 12z equals that amount. See? And last but not least, we have that there were twice as many adult tickets sold as child tickets. Okay, this one is a little bit more easy. Since it only has to do with amount, I can write that twice as many adult tickets sold as child tickets. Twice as many adult tickets were sold as child tickets. So there were more there were more adult tickets than child tickets sold. See? There are more adults. That means that I'm going to have x equals 2y. This is where the twice as many comes in. See? Twice as many is right on that too. Twice as many. All right. There I have my three equations. And now I need to solve it. See? Now, as I mentioned earlier, your two main tools are going to be substitution and elimination. Okay? I will first employ substitution. Okay? Because I think it's easiest with my equation that is way down on the bottom. Right? And so here I have my, I'm going to try to be organized, but usually this gets really funky. Okay? So I'm going to write down that this is equation 1, this is equation 2, this is equation 3. So what I'm going to start off by doing, I think would be best, is that we will plug in my third one into my first one. So if I plug in my third one into my first one, I end up with 2y plus y plus z equals 600. So that means that 3y plus z equals 600. All right. Give me a second. The other thing that I would do in line with that, see? So right now I ended up with this guy here. The other thing that I would do is plug in my third one into my second one. And now I end up with, for my second one, I end up with 15x, and so x is 2y, see? Plus 10y plus 12z equals 7,816. Okay, I'm gonna explain in a second why we're doing it this way, okay? So if you're feeling lost and confused, dazed and confused, great song by Led Zeppelin, just hang in there, see? So 15 times 2 is gonna give me 30y plus 10y plus 12z equals that nasty number, see? I combine like terms, I end up with 40y plus 12z equals 7,860. So this is the second thing I end up with. Alright, so notice, right now we did something magical. Right, I know I'm a little bit of a math nerd, but believe me, something magical is going on, brother. Alright? So what's the cool thing that's happening? Initially, these first two up here, that it? How many variables did I have? 3. The one up top had 3. The one in the middle also had 3. The one on the bottom had 2. So I plugged in this third one into both of the ones on top. How many variables did I end up with? Well, here I ended up with 2. And here I ended up with 2. And so before, when suddenly it was extremely scary that I had 3 fucking variables going around, now I only have 2. Alright, so that is the cool thing about substitution and elimination. It helps you get rid of the amount of variables. Okay, that is your main goal. If you boil it down to just one variable, then you can reach x equals like an actual number. See, like x equals 9. Like that is the kind of shit you're going for. See, but you can only do that by getting rid of the amount of variables. Alright, so that is actually the deep purpose, the deep purpose of substitution and elimination. What it does is that it reduces the amount of variables that you have going around. What we did just now over here is actually substitution. Okay, why? Because you substituted one variable for another. In this case, I no longer have x's, I only have y's. Y's and z's. See? Which was not the case earlier. Okay? So that is like the magical thing that is going on. I have less variables than before. See? All because of substitution and elimination. As you can see, they are pretty powerful tools. So the two equations that I have now are, and let me just make a little bit of space. The two equations that I have now are the ones I have boxed in. See? So let me just do it a little more pretty. I have 3y plus z equals 600. And I have 40y plus 12z equals 7,816. Right, so when I say leave it more pretty, I think it's convenient to have them aligned one with another so you can think about your approach. Alright, so I just showed you substitution. See, so you plug in one into the other and you kind of like see what happens. Right now, I could keep doing that, or I could do elimination. Interesting. Alright, because I showed you substitution, I will now show you elimination. Alright, but you can't solve it through substitution, like, don't worry about it. Alright? So, for elimination, of course, you want to eliminate a variable. See, for substituting, you substitute one for the other. That's sort of how you replace it. For elimination, you literally want to get rid of the other one. See? And so these two equations, you have to think that I'm going to be like sort of adding them. Okay? So you need to add them in a way that one of the variables disappears. And so right now, all my variables are positive. So what I can do is that I make the one on top, and again, this is by choice, but I'm going to make the one on top negative. See? So I make the one on top negative and have negative 3y minus z equals negative 600. So I multiply by negative 1 to absolutely everything. On the bottom, it stays the same. Now, if I were to add these two right now, if I were to add these two right now, would one of my variables get eliminated? I would end up with 37y plus 11z equals some number. See? So I still have my both variables. See? So that's not good enough. I need to keep going. Again, here I multiplied by negative 1. Now, if I go ahead and multiply by 12, okay, I can end up with Negative 3 times 12 is negative 36. So I end up with negative 36y minus 12z equals negative 600 times 12. God dang, bro. Pull out your calculator. 600 times 12. 7,200. See? So this is negative 7,200. All of this on the bottom, we have 40y plus 12z equals 7,816. All right, so if I go ahead and add these two now, I'm going to see that I successfully eliminated one of my variables. See? 12z is going to disappear. So so I'm going to do this thing on the left side first. So it's negative 36 plus 40y is going to give me 4y. Negative 12z plus 12z is going to give me 0. So nothing, ¿cierto? And negative 7,200 plus 7,816 is going to give me 616. And so now I end up with just one variable. Ta-da! That is what we were going for the whole time. See? So now I have only y. I get y alone, dividing by 4. Y equals whatever that is divided by 4. So 616 divided by 4 gives me 154. So y equals 154. And once you get one of them, the rest just kind of flows. See, because you can plug this in almost anywhere and it's going to work. So I can plug it in, let's say here, okay? Which means that my x equals 2 times 154, which means that x equals 308. And now for my z value, again, I can plug it in almost anywhere. In fact, I could even plug it in here. Or I could plug, actually, just to show you, I'm going to plug in x on my first one and y as well on my first one. So my first one is going to look like this. I will have 308, which is x. See? X plus y. X plus y is 154 plus z equals 600. So on this left side, I end up with, I cannot math right now, 400, 462. Yes, I choose to believe that, plus z equals 600. Get z alone, subtract both sides by 462. I end up with z equals 138. So, bada bim, bada boom, look at that. I have my x value, I have my y value, I have my z value. And that is for number 5. Again, for part A, you need to capitalize on what type of equations you can do. See? Be very general. One of them can be amount, the other one can be price. Maybe in another scenario, there's another option. Dude, like, I have no idea. See? But you gotta think very categorically for part A and approach from there. For part B, you need to remember that your main tools are substitution and elimination. And if you ever get lost in what you're trying to do, because it can get messy, remember, you are trying to decrease the amount of variables. Decrease the amount of variables until you end up with just one. And from there, it just flows. It just flows. See? So yeah, that is number 5. All right, so for this 6th one, we have that a modern art painting is contained in a square frame. Okay, perfect. The painting has a shaded region bounded by a smooth curve and a horizontal line. So this painting has, of course, what's already shaded, this. See? That's the shaded region. When the painting is placed on a coordinate axis such that the bottom left corner of the painting has coordinates -1, -1, and the top right corner has coordinates 2, 2. The curve can be modeled by blah, blah, blah. The horizontal line can be modeled by the x-axis. Distances are measured in meters. All right, so this paragraph right here, basically what it's telling you is that this line that I'm going to put right now in green is your x-axis, see? And since this is -1, -1, that means my y-axis, again, this is very just, I'm kind of like highballing it. This would be like my y-axis. and my 0, 0 would be around there, okay? So that's all it's really uh, telling you, okay? So yeah, all right. For part A, use the trapezoidal rule. Damn, the trapezoidal rule with the values given in the following table to approximate the area of the shaded region. And then this is the table that they give us. See? All right, so we need to use trapezoidal rule with that. Now, I'm sure a lot of you are thinking, God damn it, I never fucking understood trapezoidal rule. It's so flippin' weird. Let me help you through it. Okay? And so the trapezoidal rule in this case, we are using it to approximate the area of the shaded region. And so trapezoidal rule is very, very good for finding the area of a shaded region. And so why is it called the trapezoidal rule? Okay, it's called the trapezoidal rule because you can pick any sort of shape. In this case, it looks like the shaded region here. Okay, and what you're gonna do is that to find the area underneath that shape, you're gonna do a bunch of trapezoids. So I'm gonna make one trapezoid that goes like this, another one that goes like that, another one like this, another one like that. See? You're going to add all of them up, okay? And that will be your approximate area. Now it's a little bit off, see? Why is it a little bit off? Because you're missing this, you're missing this, you're missing this. See? All right, how do you know like the coordinates of your trapezoids? Well, you know the coordinates of your trapezoids because they give them to you. Okay, keep talking, Mr. Guido's math. What the hell are you saying? So you have this point here, see? -1, comma 0.6, see? Because this is -1, 0.6. So if I go ahead and put that in, it would be here. This right here is -1, comma 0.6. Okay, what is the next one? 0, comma 1.2. So at 0, we have 0, comma 1.2. Ah, and here we have our first trapezoid. All right, where's our second one? 1, comma 1.2. So that's going to be, again, this is very much, I'm just highballing it. I'm going to put it here, okay? I would say that this is 1, comma 1.2. Right, so it's the same height, and it goes something like this. And then the last one is 2, comma 0. So here we have 2, comma 0. Bada bim, bada boom. So that would be 2, comma 0. All right, so those are my trapezoids. How many trapezoids are there? We have 1, 2, 3. And so I will find the approximate area of the shaded region by adding these 3 trapezoids. How do I do that? By using a fancy formula that is called the trapezoidal rule. All right, so that's the context of what we're going to do and why. Okay, it helps me find the area. You split up a curved figure into more square-like figures. You find the area of those, add them up, boom. That's the trapezoidal area in a nutshell. Now, if we go ahead and open up our formula booklet, which I have right here, and you look for the trapezoidal rule, okay, it's right there. Now, before I go on, you, the day of the AB exam, will walk in with your brain, a very tired body, your pen, your calculator, and your formula booklet. Okay? Your formula booklet is one of the tools you can use that day. Okay? Get familiar with it. There's no use in knowing that the trapezoidal rule is here if you don't know what the heck this is even saying. Okay? And some of you probably didn't even know that the trapezoidal rule was in your formula booklet. Okay? So get familiar with it. Always use it when you study. It is an additional tool for the day of the test, and I would consider perhaps the most important one. All right, so the trapezoidal rule, what is it asking for? What is it? What the hell? So there's 2 parts to it, see? One part of it gives you the value of h, which is right here, okay? And then the rest you just kind of have to fill in, okay? So let's really try to understand what is going on here, all right? Some of these things you just have to sort of memorize, but I hope that I can help you understand better why. Okay, like why, what is going on behind the scenes, all that stuff. See? First of all, here is a sort of equal sign. See? When it's like this, it means approximate. Okay? And again, the trapezoidal rule helps you find the approximate area of the shaded region. It is not equal to the area of the shaded region. In fact, that is why in part B it says find the exact area. We're going to talk about that in a second. Okay, but just understand this is for finding the approximate area. That is why this symbol exists and why it's not equals. See? Second of all, you have integral of y dx. Okay, all that is really saying is that you're doing the integral of your function. Okay, which function is it? This line here, which is going to be my shaded area. Okay, that is what's going on. The integral is always going to be used for finding area. Then you have b on top and a on the bottom. Okay, following that intuition, b is your highest value vertically and a is your lowest value vertically. So, what is my highest value vertically here? 2. What is my lowest value vertically here? -1. And I know some of you might be thinking, shouldn't it be 1.2? Shouldn't it be, I don't know, 0? Yeah, you have a point. But the trapezoidal rule is kind of like, where are you pinging it from? And then the trapezoids go in between, okay? I can't really explain it more intuitively than that. Your B and A values are going to be your biggest and your lowest uh, values on your graph, not necessarily your line. It's kind of like the area that you're scanning. All right, fuck it. I know that is kind of weird, okay? But B is going to be your highest Y value, okay? And this is going to be your lowest Y value, okay? And so we can actually already start filling in this a little bit. B we said was going to be 2, A was going to be -1. Okay? Cool. Then you have y d of x. See? And so y d of x is going to be, again, I said, your functions here to your line. And they tell us that the artist used the equation blah to draw the curve. So this is going to be my y. Here's a y equals. And I'm going to put a dx next to it because that's how integrals work. Okay? But my y is this whole thing. See? And so if y, which I'm putting in red now, is this whole thing, then I'm going to plug in that y over here. Okay, so y is -x cubed minus 3x squared plus 4x plus 12 divided by 10, and the dx is going to go right next to it, see? All right, so all of this approximate will be the stuff on the right, okay? The stuff on the right, so we start with 1/2, okay? So that means we're good here. And then we need to put h. Now, h we said was b minus a divided by n. Or okay, we know that b is my highest y value, which is 2. We know that a is my lowest y value, which is -1. I divide this by n. Now, what is n? Let's take a moment, see? The rest of my formula talks about y0, yn, y1, y2, yn minus 1. And I know that looks really weird, okay? So let me give you an intuition. The first two on the left side, y0 and yn, are going to be your first and last y values. Your first and last y values. That is why it's 0 for first and last for n, okay? And on the other side, you're going to have all your other, quite literally, all your other y values, okay? So now that I put it like that, it's probably a lot easier to figure out. So if I go down here and I tell you to focus on this table that's in green, ¿cierto? Which I now put in black, and I ask you, my fellow viewer, what is the lowest y value that you see here? Sorry, I asked that horribly. Let me try again. What is the first? What is the first and last y values that you see? Well, the first y value that you see is going to be this one, ¿cierto? It's the one that it's most on the left. So this is y0. Okay, what is your last one? Here. So that is yn. Everything in between is going to be your y1, y2, etc. See? Now this etc. that I just call it this etc. See? This etc. is included only if you need to. See? So in this case, we actually only have y1 and y2. What do I mean by this? If this is y0, that means this is y1. That means this is y2. See? That also means, hint hint, that your yn is going to be y3. Because, you know, I'm just going in order. So this is y1, this is y2, that means this is y3. Okay, look at that. Hint hint. This n, this 3, n equals 3. Ah, okay. Let's go back up here. So we have 2 minus minus 1 is 2 plus 1 divided by n we said was 3. 3 divided by 3, h equals 1. Okay, it's coming together, isn't it? See? Let's plug in h. So h we just said is 1, so I'm going to have 1/2 times 1, parentheses y0, which we just said is 0.6, plus my last one, cierto, yn, which is going to be 0, so it's 0.6 plus 0, close parentheses, plus 2 times all my other y values, which in this case is only y1 and y2. I don't have y3 or y4 in between. My y3 is my last one. I'm putting it here. See? Okay, cool. So, whoops. So it's plus 2 parentheses 1.2 and 1.2. Awesome. So 2 times 1.2 plus 1.2. Awesome. And so I plug in everything that's on the right, ¿cierto? So this would be the trapezoidal rule. I pop that into my calculator. Okay. 1/2. I don't really need to put times 1. I'm just doing it to show it. Parentheses 0.6 plus 0. I don't need to put plus 0 either. I'm just showing like that is yn. Okay. It's always good to be organized. Times 2, blah, 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 blah. Bada bim, bada boom. 2.7. All right. And that is for part A. Now, before I move on to part B, I just made a mistake. What is my mistake here? The answer is 2.7, but I'm halfway there. Aha, I need the units. What were the units in this case? Let's figure it out. Blah, 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 measured in meters. Okay, so this is meters. Meters what? To the power of 1, squared, cubed, squared. Quick lesson. If you have units to the power of 1, it is going to be distance. If you have units to the power of 2, it is area. If you have units to the power of 3, you should know it by now, it's volume. Okay? In this case, we are talking about area. That's why it's squared, 2.7 meters squared. That is part A. Beautiful. All right, so now that we understand trapezoidal rule, what's going on behind the scenes and all that good stuff, everything else just kind of flows. See? So part A finds the approximate area. See? We use the trapezoidal rule. We're good to go. For part B, we need to find the exact area of the shaded region. See? And so, for part B, they actually give us the equation that the artist used. See? And so for finding the exact area of a shaded area, the exact area of the shaded region, we need to use an integral. Okay? An integral is the one that looks like this. See? Where we had b and a, and we plugged into a negative 1. Okay, that's the one we're going to use now. See? So actually, what's going on is that this here that I put way earlier, this is exact value. This on the right side of it is the trapezoidal rule and is also approximate, okay? Approximate value. And so for the exact value, I need to do the stuff on the left, okay? Now I'm sure some of you are thinking, God dang, I gotta fucking do an integral of that? Dude, that is nasty. Like, I can't remember well how the teacher taught it, blah, blah, blah. All right, guys, I told you you're walking in with 5 tools, see? One of them I mentioned, make memory, is the calculator, okay? So pull out your trusty rusty calculator. I'm a boomer, so I got the TI-84, all right? But you can actually do this integral very quickly with your calculator. There is, because you walk in with a graphing calculator, you should be able to do this quickly. Okay, somewhere in your calculator, there's an integral button, okay? I'm just gonna call it your integral button. In this case, for the TI-84, you press alpha, window, and it pulls up this little menu. See? You can see that here in the menu, there's different tabs. You have fraction, function, matrix, y var. See? In this case, we're doing a function. Which function? The integral one. See? So we go look for it, and here it is. F of n integral. And actually, quick tip, but I'm pretty sure you can do derivatives here too with the third one. Yeah, you can do derivatives here too. But for now, I'm just going to show you the integral one, okay? Whoops. So, alpha, window, whoops, the fourth one, and there you have, integral. So what you need to do is up here, you put your b value, which we said was 2. Okay, I'm just going to follow what I have here, okay? I plug in 2. Down here, I plug in -1. Over here, I put my whole function, ¿cierto? Since it's a fraction, I'm going to do alpha y equals, pick the first one. Again, alpha y equals for fraction, pick the first one. And now it's a lot easier to plug in. So I'm just going to go ahead and put everything. Trust the process, it always works. Yada yada. Whoops. Bada bim, bada boom. D of my variable, in this case is x, d of x. So there I plugged in everything. I can go ahead and press enter. It calculates it for me, and my exact value is going to be, following the calculator, 2.925. I am missing something. Correct. The units. Squared. Why is it squared? Because we're talking about area. Boom. That is part B. Say no more. We move on. Part C. Find the area of the unshaded region in the painting. Ooh, god dang. Alright, that's a little bit weird, isn't it? So, what we did, again, context. See, what we did just now with the trapezoidal rule is that these figures I drew in red, we calculated that the area of this, from part A, ¿cierto? Is that it's, how much was it? 2.7, see? 2.7 meters squared. From part B, we found that the shaded area, ¿cierto? Which is like actually everything, the exact value, was 2.925. For part C, which they're asking for the area of the unshaded region, okay, we need to find everything that's in white, see? So I don't really have like a white color, but I can tell you that we need to find the area of this and the area of this, see? Okay, so something convenient here is that because I have the area of the shaded region, I can just take the whole box and subtract what's here, see? So, what is the area of the whole box? Well, is it a box? Is it a rectangle? Aha, this is where context matters. Read again the problem. What did I highlight initially that I found important? It's a square frame. So a square, these values are all the same. Aha, okay, so what is from here to here? Well, if this is -1 and this down here is 2, that means I have from here to here I reach the 0. Fuck it, I didn't explain myself very well. Point is, if the bottom left side of my square has -1 for my x, and the other side has a 2 for my x, that means I have 3 units here, see? Because if you make a number line and you go -1, 0, 1, and 2, how many times do you jump from -1 to reach 2? You jump 1, 2, 3 times. So that is why it's 3 units. So the side of my square is 3. And because it's a square, that means this is also 3. And so what is the area of a square? It's going to be base times height. I think that's in your formula booklet. Actually, that's probably not. Area of a blah, blah, blah. Yeah, area of a square is not here. Pero I do think it's very easy to memorize. It's just base times height. See, actually parallelogram. That is sort of like a square. So A equals base times height. Yeah, well, so the area of the whole thing, ¿cierto? Area whole thing is 3 times 3, which is 9. So area of the whole thing is 9 meters. All right, cool. The exact area we found was 2.925. So if I go ahead and do 9 minus 2.925, it's going to give me the area of the unshaded region, which will be 6.08 meters squared. And if you want to put the exact value, it's going to give you 6.075. I was just doing significant figures up top. See, but either of these works. The essential part is identifying that it is a square frame and working from there, finding the distance of the square and finding the area. I hope that after this exercise you see that the trapezoidal rule is spooky, but it's really not that like fucked. You know, if you understand that this left side is first and last y values, and that the rest is everything else, and how to find n, I feel like you're good to go. Okay, so really get familiar with what's in your formula booklet. Understand the formulas. Don't just know that they're there. Okay, but yeah, that is for number 6. All right, and now for the 7th one, we have that Leo is investigating whether a 6-sided die is fair. So whether a 6-sided die is fair. He rolls the die 60 times and records the observed frequencies in the following table. So here we have number on the die and observed frequency. What does that mean? So he threw this 60 times. See? Of the 60 times, the amount of times he got a 1 on the die was 8. The amount of time he got a 2 on the die was 7. The amount of times he got a 5 on the die was 12. Okay, so those are observed frequencies, not expected. We have that Leo carries out a chi-squared goodness of fit test at a 5% significance level. For part A, we need to write down the null and unalternative hypothesis. And so for part A, okay, this all really depends on how you set up your approach. See? But what it will revolve around is what your guy is trying to investigate. And so Leo is investigating whether the 6-sided die is fair. So fair means that it's honest, you know, it's not like it's some bullshit die that's like charged to one side or the other. We might, for example, figure out that it is a charged die because we only got 6 times number 3. And you would expect number 3 to show up a lot more. And so is it fair? That's the question. Or was it just a game of chance and, you know, it's, you know, maybe it is fair, maybe it's not. Like, we gotta figure it out. See? This could have been within the realm of possibilities, or it could be bullshit and it's not fair. See? So that is the sort of thing we will find out. All right, so for part A, write down the null and alternative hypotheses. And so basically for your null, okay, and your alternative, one of them is like what I'm investigating is true, and the other one is like what I'm investigating is not true. Okay, it's very important that for your null hypothesis, you will write hypothesis. You will write it on H0. Okay, that is like the technical way to put it. And so for H0 in this case, I will put that the die is fair. Okay, your alternative hypothesis, again following its name alternative, it's the other option, is always going to be the opposite. Okay, opposite of H0. And so whatever you put in H0 with the word not, okay? So my H1 is actually going to be that the die is not fair, okay? So that is a cool way to sort of remember what to put in H0, what to put in H1. One of them has to have the word not, okay? And everything else is the same, Okay, so I'm just going to put that for H0, that the die is fair. For H1, that the die is not fair. That is for part A. For part B, we need to write down the degrees of freedom. Okay, degrees of freedom. What the hell is this? And so degrees of freedom, which actually, I'm not sure if it's in your formula booklet. Probably not. It's not in your formula booklet. Wow, that's mean. Okay, this is the kind of thing. This is the part of the IB I don't really like. You need to memorize this, okay? It's one of the few things you actually have to memorize. So degrees of freedom, um, intuitive. I'm just gonna share the intuitive idea. Okay, so intuitively, it's gonna be. It's sort of like rows minus 1 times columns minus 1. Okay? Just stick to that and you're going to be fine. This is going to be your degrees of freedom. On a more technical level, it helps to know how to carry out your chi-squared test. Okay? I'm not going to dig into that because you're probably not interested in that. Okay? But intuitively, your degrees of freedom is going to be rows minus 1 times columns minus 1. So how many rows do I have? I have 2 minus 1. How many columns do I have? I have 1, 2, 3, 4, 5, 6. Okay. So that means I have 6 columns minus 1. That means I have 2 minus 1 is 1. 6 minus 1 is 5. 1 times 5 is going to be 5. So degrees of freedom is going to be 5. That is part B. Part C, write down the expected frequency of rolling a 1. Okay, so here there is a difference we need to learn. We have expected frequency here, and we have observed frequency here. Okay, and so if this excited die is 100% fair and you are in a perfect world, that means the amount of times you rolled 1, 2, 3, 4, 5, 6 is always going, in this scenario, okay, is going to be 10, 10, 10, 10, 10, and 10. I'm going to tell you in a second how I found that, okay? And so this has to do with the following. A 6-sided die, see? Let's talk about probabilities for a second. I know you guys don't like probabilities, but deal with me, okay? So you have, okay, so there's gonna be number on die, and down here is gonna be probability, okay? So number on die we have 1, 2, 3, 4, 5, 6. Okay. So if this is a die and it's a normal die and it's a fair die, what is the probability of rolling a 1? Well, a die has 6 sides, see? And so one of the sides is one of the sides, and there are 6 others. So the probability of rolling a 1 is 1 over 6. The probability of rolling a 2 is also 1 over 6 because it is just an additional side of the die, see? And so you actually do a probability of 1 over 6 for all of these, okay? All right, so that is the probabilities sort of side of this whole thing, see? Over here on the right, in red, I forgot to write, sorry. In red, we also have number on die, okay? Number on die, and down here we have expected, okay? So how did I reach 10? Well, the expected has to do with the amount of times you do your trial. So, my guy Leo, okay, my guy Leo, how many times did he roll the dice? He rolled it 60 times. And so, what is the expected amount that I get for a 1, for rolling a 1, cierto, of those 60 times? Well, the probability of that is 1 over 6. So I'm going to take 60, multiply by 1 over 6, and this will give me 10. You can trust me on that, or you can double check with your calculator. 10 times 1 divided by 6 will effectively give you 10. Okay, so that is expected probability. I do the same for the rest of them. This is my expected table. See, this is all just doing 1 over 6 times 60. That is how I reached that. See, awesome, cool. So the expected frequency of rolling a 1 is just going to be 10. I guess my answer is over here, ¿cierto? It's going to be 10. Now we get to the juicy part. See, now we get to the part where we say find the p-value for the test. God dang. All right, now we got to do the hardcore stuff, you know? All right, so which test? I know it might sound kind of duh, but which test? Let me just write C over here. It's a little bit of a talk I have. This is to be C. Down here, okay, so C is up there. Now for part D, find the p-value of the test. So first thing you need to ask yourself is which test? Then you need to say, what do I need? And then you just fucking do it, okay? So, which test is it? Here it says that Leo carries out a chi-square goodness of fit test. See? Now that tells me more than what you think. It's chi-squared goodness, goodness gracious, goodness of fit. What do I need? We're about to find out, and then we need to do it. See? So it's a chi-square goodness of fit test. So I put up my calculator, see? I go to my testing area, which is going to be stat, at least for the TI-84, it's going to be stat and tests. Here are a shit ton of tests. Find the chi-squared one. Go all the way down, and here it is. So here we have chi-squared and chi-goff. Which of the two might it be? Ah, well, it literally says that we are doing a goodness of fit. GOF. Here we pick the Goff one. Then we see that we need observed and expected. L1, L2. So what do I need? I need L1, I need L2, and my DF. See? Alright, so, well, the DF is already on 5. So this could have been 3. Okay, so I should always put the correct DF. In this case, it's 5. How do I know? I know from part B. Alright, cool. So there I got my DF. See? Awesome. So we are good there. Now I need L1 and L2. How do I find L1 and L2? Go to stat and edit. Okay, this is the kind of thing you have to memorize. You go to stat and edit. Here are my lists. L1 and L2 are up here. See? One of them is observed, the other one is expected. Which one was which? We go back because our memory is fragile. L1 is observed, L2 is expected. Okay. Here is my observed list. So this is going to be L1. And up here from part C is my expected one. And that is going to be me, blah, 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 blah. That is going to be my, that is going to be my expected list. Okay, the one on the bottom, the one that is a bunch of 10s. So I'm going to put that in my calculator. See, stat, edit. I erase my old lists. So I clear it up here. I clear it up here. Yapple. L1 has to be 8, 7, 6, 15, 12, and 12. Take a second, double check. Looks beautiful, just like you today. L2 is going to be 10, 10, 10, 10, 10, 10, 10. Great anime. Go Naruto. Alright. And now we gotta, well, now that we did L1, now that we did L2, and we have DF, now we need to do the test. Alright, cool. Stat, test, chi-squared goff. Bada bim, bada boom. Everything is correct. Calculate. Let's go. There we go. Alright, so what the hell is going on? What did this give me? Well, it gave me my chi-squared value. Okay, so I know that my chi-squared is going to be 6.2. My p-value is going to be 0.287. 241. Okay. And my DF, as I mentioned earlier, not really necessary that I write it, it's going to be 5. And then there's CN tier B. Just don't worry about that, okay? This is all you will probably ever need. All right, so write down the p-value for the test. Well, the p-value for the test, as we just found, is this guy here. And since we like significant figures, it's going to be 0.287. You can write down the whole number, it's fine. See? How do significant figures work? Well, I go to 1, 2, and 3. I compare this one to the one on the right. Since it's 4 or lower, that means I keep it at the number that it is. I end up with this. Okay? Cool. 0.287, 0.287. Cool. So, Apple. Part D is going to be 0.287, or if you want the long version, it's going to be the long number we just found. Blah, blah, blah. All right, cool. Part E, state the conclusion of the test. Give a reason for your answer. So notice this. There are 2 points here. See? Small detail, but there are 2 points here. One of them is the conclusion of my test. One of them is the reason for your answer. Okay? That means you can conclude it incorrectly, but still give a reason and get half a point. Or at least 1 point. See? Or you can, do the whole process wrong, but conclude correctly and still get a point. Okay? So even if the numbers don't make sense to you with the process that you're doing, if you conclude correctly, you can get a point. Okay? You can get the whole IB answer, your whole IB test pretty much wrong, but if you follow the process, they're going to give you points for process and you end up with at least a 4 or a 5. Okay? I'm exaggerating. You're not going to get the whole test wrong, but I am pointing out that the process matters a lot. Okay? So do the conclusion with whatever your hypotheses were from part A and trust yourself and trust the process. Okay? You're going to get a point for it at the very least. All right, so state the conclusion of the test. How do I conclude this? Well, a good rule of thumb, okay, is that you need to compare the significance level to your p-value. See? And so it all depends on, I'm going to do this over here. See? It all depends on whether your p-value is greater than your percent of your percent significance level. It also matters if this, instead of significance level, is a critical value. Okay, all of that shit matters. See? In this case, if my p-value is greater than my significance level, this means that how do I say it? I'm just gonna write it out, okay? This means that we have insufficient evidence to reject the null hypothesis. And so all you're really doing is seeing whether you reject or approve the null hypothesis, see? And so if my p-value is greater than my percent significance level, that means that we have insufficient evidence to reject the null hypothesis. All right? And so what is my p-value? Well, my p-value we said was 0.287. And is this greater than or less than my significance level? My significance level we said was 5%, which means this 0.287 is greater than 0.05. So effectively, we have insufficient evidence to reject the null hypothesis. See? For concluding this kind of stuff, see, this is my conclusion, okay? And this is my reason down here. See? And that's it. All right? That is number 7. All right? I will say though, for the null hypotheses, for concluding on all that good stuff, I recommend you memorize some of this stuff. See, like if you memorize this, the day you get the opposite scenario, you just flip it, ¿cierto? Instead of putting reject, you put approve, ¿cierto? Or you say that there is sufficient. See? But again, unfortunately, this is the sort of thing you do have to memorize. And the other thing that some of you are probably thinking of is, why the hell is this 0.05? See? Well, quick class. If this, sorry, for percents, okay? Remember this. 1 is 100%. 0.5 is 50%. 0.05 is 5%. Okay, if you remember these 3 values, you can figure out any percent immediately. In fact, if I right now tell you what is in percent 0.287, you can, maybe you take a minute, but you will tell me that it's 28.7%. Alright, so yeah, to make these comparable, the p-value was in decimals, see? Gotta convert it to percent, or convert this percent to a decimal, which is what we did. Alright? Whatever you do, this is how you approach the problem. Protocol matters a lot. Notice the context of the problem. The small word goodness of fit goes a long way to figure out which one you need to do. Yeah, whatever, man. That's number 7. I hope it helped. All right, and now for the 8th one, we have that. A factory. A factory produces bags of sugar with a labeled weight of 500 grams. The weights of the bags are normally big words, normally distributed with a mean of 500 and a standard deviation of 3 grams. Part 8. Write down the percentage of bags that weigh more than 500 grams. All right. There's a couple ways to do this. See? I think the first one, which allows me to talk about the normal distribution, is going to be the most useful one. So, this stuff is normally distributed, okay? That means that we have something that looks a little bit like this. Okay, and the cool thing about normal distributions is that they follow a certain sort of pattern, okay? You're going to have right down the middle, you're going to have your mean, okay, which is written like this. So that's going to be my mean. And every certain amount of standard deviations over, so for example, this is going to be my mean plus 1 standard deviation, we're going to have, a certain amount of percent. Over here it's 34%. And if you actually go back, so 1 mean minus a standard deviation, you also have 34%, okay? And so what's kind of cool about the normal distribution is that all these percents are defined from before. See, so if over here it's, I don't know, 19%, I don't remember the number, over here it's also 19%. So that means that for finding area and probabilities of landing a certain number, because it's normally distributed, you can like really work around this fact, see? In fact, if you literally just Google this, you're gonna find that exacto normal distribution looks something like this. See, and there you can see how you have 1 standard deviation over, 2 over, 3 over, and there you have those percents I was talking about. 34% is 1 over. 13.6 is 2 over. So instead of 19, I was mistaken. 13.6. All right, whatever. See, and so that's sort of like how it looks like. Okay. Now notice one thing. If I finish filling up these percents, here I have 2.1, here I have 0.1, and I add up these ones on the right, okay, I'm going to have 34.1 plus 13.6 plus 2.1 plus 0.1. That gives me 49.9, see? So it's basically 50. It's basically 50, see? So that means that if I add all the values on the right side, I basically get 50%. Okay, that's the cool thing about the normal distribution. See, I'm going to draw it again. Right here you have the mean, okay, and all of this in pink is 100%, okay? Which means that what I'm going to put now in light green is 50%, okay? So for part A, write down the percentage of bags that weigh more than 500 grams. Well, my mean is 500 grams, so everything to the right of it is going to be what I'm putting in green, because right here we have 500. And so the percent for part A is just going to be 50%. I'm about to show you a different way to get to that. Just give me a second, okay? Later on, they tell us that a bag that weighs less than 495 grams is rejected by the factory for being underweight. And we need to find the probability that a randomly chosen bag is rejected for being underweight. And so if my randomly selected bag weighs less than 495, it is rejected. See? So that means I need to sort of find the number that goes roughly, very roughly, from like here to here. See? So that is the area that I'm trying to find, or the probability. Hint, big hint. Area under a curve equals probability. Okay? Area under a curve equals probability in this case. So we're trying to find the stuff in orange with this little bit here being 495. So basically from 0 to 495, I'm going to be highlighting this whole thing in orange. That is the area that we're trying to find. And so it's pretty clear what we need to do. See, we need to find the area of the thing in orange. But what can be much more useful, especially the day of the test, is understanding which tools you have at your disposal. You do have your formula, you do have your graphing calculator. Yeah, and your graphing calculator has a whole ass section with distributions. Dead ass. So if you go ahead and press second with blue and the vars, you hit that distribution button. See? So once I'm here, I have three main tools that I need you to focus on. You have normal PDF, normal CDF, and inventory normal. See? The next couple minutes is going to be me going over each of these. Okay? And so for PDF, you're going to be using PDF for, you have the question, what is the probability of getting X number? See? So this is for PDF. See? Normal PDF. If you have the question, what is the probability of getting a number between X and Y? This is going to be CDF. All right. Finally, if my probability or area is X, what is my Y boundary? You will use inventory normal. Okay. For this exercise, we will be using CDF and PDF. All right. Now, you can memorize this. Okay, you can memorize this. What is PDF? What is CDF? What is inventory normal? And you're good to go. What I suggest is that you play around with it and get to know your calculator. See? So if you press normal PDF, what does it ask for? It asks for a Y value. That symbol in the middle is mean, and the symbol in the bottom is standard deviation. And so if you give it all of that, it's going to give you the probability of landing that number exactly. Okay? That being said, if I look at normal CDF, whoops, if I look at normal CDF, I see it asks for a lower, an upper, the mean, and the standard deviation. And so the lower and upper makes reference to the between I'm talking about, between X and Y. See? So basically, I would take my normal distribution, and I would ask, say, from here to here, what is the probability that I land the number that is in here? See? And so that would be my X, that would be my Y, that would be my lower, that would be my upper. All right? And so that is actually what we're going to use for part B. See? So for part B, what is my lower? Well, since we're looking for bags that get rejected, see? Bags that get rejected weigh less than 495. So my lower is going to be 0. And my upper is going to be 495. All right, cool. So I can actually go lower is 0, upper is 495, my mean is 500, my standard deviation is 3. How do I know that my standard deviation is 3? Context. Context matters. Buzzwords matter. What did I highlight initially? Mean is 500, standard deviation is 3. Okay? Okay. Go ahead and paste. There you go. It is that. See? So for part B, I'm gonna put it down here. So for part B, we found, all right, we found 0.0477903, which is the same as in significant figures 0.0478, which if I put it in percent will be off, my bad, it will be 4.78%. Okay. If you're not sure how I did this jump here, remember this: 1 is 100%, 0.5 is 50%, 0.05 is 5%. As long as you remember those three examples, you can figure out virtually any percent out. See? The big trick is multiplying or dividing by 100. Okay. Yep, well, that is for part B. See? Before moving on to part C, let me show you a little bit how you can use CDF for part A. Vale? So for part A, it's write down the percentage of bags that weigh more than 500 G. So that means that my lower is 500 and my upper is, like basically positive infinity. See, like anything above 500. And so what you can do actually is pull up the CDF, put lower 500, upper, just put like a really big number, like that's basically infinity. Go ahead and paste. That's basically 50%. There it is. See, so that's another way to figure out part A. Again, I'm just showing you so you get familiar with your tools. PDF is probability of getting a specific number. CDF is lower and upper bounds. And inventory normal is if you have the area and you're trying to find your boundaries, which is part C. So for part C, we have that a bag that weighs more than k grams, okay, is rejected by the factory for being overweight. The factory rejects 2% of bags for being overweight, and we need to find the value of K. All right, interesting. So here we have the area. What is the area? Well, I said that area has to do with probability. 2% of bags, see? 2% or 0.02, okay? Get rejected for being overweight. Now, if I imagine a little bit, ¿cierto? My distribution, okay? We have this 2% being way at the very top. See, this is 2%, see? All right, interesting. So what number is that? Well, let's figure it out. So I have my probability. See, so I have to work around that. I have inventory normal here. The area we said was 0.02. See? The mean, we're going to say is 500. Standard deviation is 3. Go ahead and plug it in. This is what I get. See? Now, I got 493. So that's interesting. See, I got 493, which is, if my mean is here 500, I got 493 over here. Something is wrong. See? Well, this is where it gets super interesting. See? You need to understand what you're asking your calculator. If you plug in for the area 0.02, at least in the TA84, I know some more modern ones have different options you can go around it, but for the TA84, when you use inventory normal and put in 2%, you're asking it to go from 0 to 2% and to spit back the x value, ¿cierto? So essentially, you're asking your calculator when you plug in 0.02% is that you're telling it, okay, so go from 0%, reach 2%, and give me that x value. See? And that x value, the calculator told me, is 493. See? 493.83. And so what it's actually giving you is the weight of the bags that are the 2% that weigh the least. So the most underweight ones, the ones that weigh the lightest, that are within the 2% realm of them, is 493 grams and below. Okay, that is what I just found. And so if I want to go for the 2% over there, ¿cierto? Actually, since this is 100, would need to plug in 98% here. Ah, context matters. Wow. So, distribution, inventory normal. I plug in 0.98, go ahead and paste. It gives me 506. And so the x value of my bags that weigh, that are in the top 2%, so the ones that weigh the most, in the top 2% are 506 grams, 0.161, and up. See? And so for part C, the bag that weighs more than k grams that gets rejected for being the top 2% are any that go or that have the weight of 506.161 grams or up. See? So it's in 3 significant figures, we would say it's 506. Don't forget units, grams. All right, so that is for number 8. I think the most important thing, in my opinion, honestly, is understanding your 3 tools. If you understand what PDF, CDF, and inventory normal do, and intuitively when to use which, dude, you're good to go, straight up. That is for number 8. All right, and now for number 9, we have that the function f is defined by this whole thing. Okay, part A, find that. What the hell is that? When they write it like this, that will make reference to the derivative. So that is actually the derivative of f. Okay? Another way in which you might see it was like that. Okay, so it's your function f doing the derivative of in respects to x. See? So yeah, there's a couple different ways you can see it. You might also see it like this. D of f, d of x. Okay, I'm just very used to seeing that symbol like that. Maybe it's just a fancy D, I have no idea. Alright, but fuck it. Those are the kind of things you can encounter. Alright, so part A is just asking for the derivative. Now, thankfully, at the IB Math AISL level, the only derivative we're going to be encountering is the exponents one. See, so as long as you understand the exponents one, you will be good to go. So let's go with the simplest example first before jumping into part A. If I have f of x equals x squared, okay, the derivative of this is going to be that you take the number up top, put it down in front, and do a -1. Dead ass. So I put the 1 on top, I put it in front, and I do a -1. So 2 minus 1 is going to be just 1, which is the same as just 2x. See? Yeah, that is the derivative of x squared. And so what is the kind of shit that can happen? Well, let's say that from before I had like I don't know, let's say instead of being like this here, see? Instead of being like this, I have, say, 2x squared, see? So that means I'm going to have this 2 coming down in front. So that means I have 2 times 2. That means this would be 4. Okay? And lastly, if this instead of 2 were, say, 3, that means this guy is going to be 3. That means that 3 minus 1 is going to be 2. That means I end up with 4x squared. Alright, so that is for the derivative, like just in general, ¿cierto? Of the exponent. See? And so for part A, they immediately, because they're the IB, they immediately throw us a curveball. F of x has an x on the bottom. Dang, bro, what the hell do you do with an x on the bottom? Alright, so part A. There ain't no mountain high enough, right, boys? Come on. 2 divided by x plus 3x squared minus 3. So before, notice my language, before you do the derivative, if you ever have a variable on the bottom, do this right away. Okay, don't make it hard on yourself, especially if you're doing a derivative. Do this. See? Another way to write that is to put 2 times x to the power of -1. So right now, I haven't actually changed anything. I just changed how it looks like. Okay, but it's still the same number. This x being on the bottom is the same as x to the power of -1. If you're confused, I have no idea what the hell is going on, let me show you a math pattern. See, I'm a little bit of a nerd, so you're gonna have to deal with me. All right. 2 to the power of 3. How much is it? 2 times 2 times 2. Very good. 8. 2 squared. 2 times 2, 4. 2 to the power of 1. 2. 2 to the power of 0. Ah. 2 to the power of 0 is 1. Okay. 2 to the power of -1 is 1 over 2. 2 to the power of -2 is 1 over 4. Okay, there's a couple different ways to like sort of remember. Oops. There's a couple different ways to remember this pattern. Okay. The one that I like the most is to notice that as my exponent is decreasing, see, by 1, what am I always doing? I am actually dividing by 2. Dividing by 2. Dividing by 2. And that is also why, flash lesson, anything to the power of 0 is going to be 1. Because by dividing by itself, it will always reach 1. See? And so when you have a negative exponent, really you're just dividing it by 2 in a weird sort of way. See? In this case, it's by 2 because my base is 2, ¿cierto? I'm talking about this guy here, like I divide by 2 because this is 2. But if it were 3, I would divide by 3, etc. If you want to go back up, you multiply, see, by your base. Okay, so that is just a flash lesson on exponents and that sort of pattern that shows up. And so that is why if you have an exponent on the bottom, to put it up top, you just do the negative exponent. See? Awesome. I'm going to show you one more thing. I don't think you're going to encounter this, but if you ever do, now you know. See? If you have that f of x is, I don't know, 4 divided by x squared, what would this be writing it in the form that we just did? Well, the 4 stays up top. And if I want to put this on top, it would be x to the power of negative 2. See? And so the negative is sort of what makes it flip. Okay? As long as I have negative, it's going to be flipped. All right? So yeah. Now that we have that in mind, we can do the derivative more easily. So if I apply the derivative now, all right, this negative 1 is coming down to the, is going to multiply on the bottom, so it's going to be negative 1 times 2. This x is going to be negative 1 to the power of negative 1 minus 1, see? This 2 is going to come down to the 3, so it's going to be 3 times 2, x to the power of 2 minus 1. And this negative 3, what happens? It just, it, it turns into 0, see? That is something that derivatives itself have that you need to keep in mind. If you ever have what they call a constant, okay? If you ever have a constant and you're doing a derivative, that constant pretty much disappears, see? That is because this guy is not accompanied by an x or anything likewise, and so this 3 just disappears. Okay, that is a rule of thumb. When you do the derivative, you only really care if your term has, you know, the variable you're doing the derivative of. So if in this case it doesn't have an x, you consider it a constant and it's just going to be plus 0 once you do the derivative. Okay, and so this negative 3, technically, we don't really care about. All right, so I keep going. See? This negative 1 times 2 is going to be negative 2. This x to the power of negative 1 minus 1 is going to be x to the power of negative 2. Plus 3 times 2 is going to be 6 to the power of x. Oh, sorry, with x to the power of 2 minus 1, which is just going to be 1. See? Which is the same as putting nothing. So that, ladies and gentlemen, is the derivative of part A. If you want to leave it how it was originally, you put this down in the bottom, ¿cierto? Which would be negative 2 divided by x squared. See? Plus 6x. Alright, so now I hope you understand a little bit better what happens when the exponent is negative. See? You just kind of like throw it on the bottom or throw it up top, depending on the scenario. Alright, that is part A. Part B is really weird. Okay, I'm just going to say that right now. It is really weird. It says to find the equation of the normal to the curve. God dang, bro. Of the normal to the curve. So, what is the normal to the curve? This, I'm just going to assume, looks a little bit like a parabola. Okay? What I'm about to do now is really to explain what normal to the curve means. Okay? So you can have x and y. Let's say you have a line that looks, I don't know, whatever, like this. And I say, find the normal to the curve at x equals, I don't know, 3. Okay? This is different from the example. This is just to make a point. Okay? And let's say that my 3 is going to be uh, here. Okay? Yeah, but so if x equals 3 is here, what's going on? First, I have my tangent. Okay? So this is, in orange, is going to be my tangent. What is a tangent? Something that touches my line at one point and then just keeps on going. See? So that would be at x equals 3. See? Right here is x equals 3. So that would be my tangent. What is my normal? My normal is perpendicular to my tangent. So this would be my normal, okay? So my normal is perpendicular to my tangent. That means two things. First of all, this now is all 90-degree angles between one and the other. And also because it is perpendicular, something I showed I think on number 4 if I'm not mistaken, or 3, is that you have a couple types of lines, see? And in terms of slope, you have parallel lines and you have perpendicular lines, see? Just nice and quick, parallel lines have the same slope, so m1 equals m2, while perpendicular lines have a reciprocal slope, see? The fancy math language would be that m1 times m2 has to equal -1, okay? That is the fancy math language behind it. What I prefer to do is that really you just flip it and multiply by a -1, see? Or just by a negative. So let's say if my m1 is whatever, 2, and I say that my first slope is perpendicular to my second one, how do I find the second one? Well, first I flip the first one, ¿cierto? So I flip the 2, so 1/2, and I multiply by a negative, see? So m2 in this case would be -1/2. So this would be perpendicular slopes, okay? Let's see what happens in the exercise down here. They tell us to find the equation of the normal to the curve, okay? So that would be, the perpendicular thing and all that stuff. At 1, 2 in the form blah, blah, blah. So what is actually kind of cool about this is that when you do the derivative of something, okay, you are now finding slope. What do we make this? Originally here, okay, you were finding sets of points. What do I mean by this? If you plug in x, you would find a value for f of x, and this would help you plot lines on a graph, see? So this would be a bunch of sets of points. It would be like x and y, etc. See? You would get a bunch of different x and y's. When you have the derivative, it's a little bit different. Because now, when you plug in x, you are asking, what is the slope at that point? At that x coordinate would be the very fancy way to put it. What is the slope at that x coordinate? See? This is after you do derivative, after derivative. See? When you plug in x, you are asking what is the slope at that coordinate. So if I go ahead and plug in 1 at my derivative version of my function, I am asking what is the slope when x equals 1. See? Why did I plug in 1? Because they are asking for the normal at 1, 2. See? So, I'm going to use this guy here. Dale. We have -2 times 1 to the power of -2 plus 6 to the power of 1. So my first term is just going to be -2 divided by 1 squared. See, I'm applying the negative thing first. All right. Plus simply 6. So what is 1 squared? Well, it is 1 times 1, which is just 1. So I end up with -2 over 1 plus 6. Same as -2 plus 6. Same as 4. So 4 is the gradient. See? Now it's the gradient of what? It is the slope of what? This would be the slope of the tangent. See? So it would be the slope of the tangent, the guy in orange. To find the slope of the normal, which is in red, I need to flip it. Oops, let me put it in red so that I'm consistent. I need to flip it and do the negative. Okay, so I'm gonna flip it. So it's 1 over 4. And do the negative times -1. I end up with -1 over 4. So this here is going to be slope of normal. See? So I'm almost done with this exercise. I need to find the equation of the normal, see? To find the equation of a normal, there's a couple ways to create it. I'm going to go ahead and go to create. There. To find the equations of a straight line, I have 3 options, see? I have y equals mx plus c, ax plus y, whatever. I have 3 options, okay? The one that I suggest the most is the last one, see? It is called the point slope formula. what do you need to make it work? You need the slope and you need a set of points. If you have that, you are good to go. Where did I find this? In your formula booklet. The formula booklet you will be using the day of the test, so get familiar with it. Alright, so the point slope formula looked like this. Y equals, sorry, y minus y1 equals slope, parentheses x minus x1. Okay, so what set of points can I use? What is going on? Since they ask us at this point here, that is my x1, y1 that I can use. So I can do y minus y1, cierto, this 2 here, equals the slope, which I just found to be negative 1 over 4, parentheses x minus x1, which is just 1, and I can solve it from here, see? So I end up with y minus 2 equals negative 1 over 4x, because I just distributed, plus 1 over 4. Cool. Now I'm not quite done yet, because they want us to put it in the form of this, see? This is called standard form. So there's two things going on. First of all, it all needs to be on one side, see? Notice that there's that 0 on the right side. That means everything else goes on the left side, see? So we're going to do that first. And second of all, they all have to be an integer. See? The z here means that it has to be an integer. What is an integer? It is whole numbers that can be negative. So an integer would mean negative 2, negative 1, 0, 1, and 2. See? So it has to be whole numbers. All right. This step here, since I need to throw it on the left side and have it be in integers, okay, and have it be in integers, I suggest that you make it all integers right away. See, it'll make it easier to move stuff around, etc., blah, blah, blah. So, since I have fractions going on and they both have a denominator of 4, how can I get rid of a fraction? All you need to do is multiply by the denominator, period. So the denominator here is 4. So if I multiply everything by 4, things will happen. See, let's see what happens. For example, my first term, see, is going to be 4 times y. My second term is going to be negative 2 times 4. My third term is going to be 4 times negative 1 over 4 times x, see? And this last one is going to be 4 times 1 over 4. And so what does multiplying by 4 do, cierto? I end up getting rid of this guy with this guy, and this guy with this guy. And suddenly it's a lot more easier to handle. So, over here I end up with 4y. Over here I end up with negative 8. Over here I end up with negative x. Over here I end up with plus 1. And so since I needed everything on the left side, see, I'm going to go ahead and do plus x, x plus 4y minus 8 equals just 1, cierto, positive 1. I need to have it equal to 0, so I do minus 1 on both sides. I end up with x plus 4y minus 9 equals 0. And that is how you turn into standard form. See? That is for number 9. Again, keep in mind how the derivative works, how it can be written as well, cierto? Understanding that when you plug in x, you're asking what is the slope at that x coordinate. It's a little bit different. And lastly, that the equation of the normal is this weird thing which is perpendicular to tangent, okay? If you want to memorize it that way, the normal is perpendicular to the tangent, I'm not saying that it's intuitive, but I am saying that you have to know it. That is for number 9. All right, for number 10, we have a tree diagram. See, we have my good guy Carl, who has 3 brown socks, okay, and 4 black socks in his drawer. He takes 2 socks at random from the drawer. 2 socks at random. Okay, we need to complete the tree diagram. So let's go in order, see? For example, up here, also I'm going to explain the tree diagram a little bit, what goes on behind it, etc. See? So up on this first set, see, focus on what I'm drawing now in green. Just focus on this, forget the rest, okay? So this is the first sock he takes, okay? as it says up here. The first sock he takes, he can either pick brown or black. So initially, there are 3 brown socks. That's where this 3 comes from. And there are 4 black socks. That is where this 4 comes from. See? And so that is why the 3 is there. That is why the 4 is there. Why is the 7 there? Because the total amount of socks is 7. How do you know? Well, you have 3 brown plus 3 black. That gives you 7. Oh, fuck, sorry. 4 black. And that gives you 7 total socks. Okay? So that's where the 7 comes from. All right, I know for some of you this might be kind of duh, but it's good to know later to understand why this 7 changes to a 6. Interesting. We'll get to that in a second. Yeah, and the last thing I'm going to mention, okay, before we move on, whoops, I erased this by accident, is that this probability plus this probability equals 1. Okay, that is something that always has to happen. This plus this equals 1. Every sort of like stem, so this one in red or this one in brown or tan, has to equal 1. So this plus this, for example, actually I should use red. This plus this, how much does it give you? It also gives you 1. Oh, interesting. Okay. And so there is those are like the rules of the tree diagram. See, as long as you keep those 3 rules in mind, the thing that it adds up to 1 in every one of the stems, the thing that this gets subtracted by 1 because one event follows the other, that kind of stuff is what you need to know or keep in mind. See? So, Yapo, we completed or we understood much better what is going on for the tree diagram. What we need to fill out is this stuff on the bottom, see? And so if on the bottom I pick the black one, see? How many black ones do I have left? Well, if I used to have 3 brown and 4 black, okay? For the path, like initially, ¿cierto? For the path on the bottom, I now have 3 brown and 3 black. Okay, so if I have 3 brown and 3 black after this first step, ¿cierto? After this first step, that means that down here for black, I'm going to have 3 out of 6, and for brown, I will also have 3 out of 6. And there, that is part A. I completed the tree diagram. Okay, now it gets a little more juicy. See? For part B, we need to find the probability that Carl takes 2 socks of the same color. Okay, so when we're talking about probabilities, you need to consider the scenarios that can occur. Okay, so scenarios that can occur for same color. I either pick brown, brown, or either pick black, black. There's another scenario that confirms that Carl takes 2 socks of the same color. So, what is our probability that Carl picks brown, brown, and probability that Carl picks black, black? See? That is sort of my approach, okay? But, I will push you to do the following, okay? A lot of people have trouble understanding when to add probabilities and when to multiply them, okay? So I will first say this. If it says and, I mean, if you think an and, then you will multiply. If you think an or, you will add. And so if I really, really force myself to use that language, the probability that Carl takes 2 socks of the same color, thinking of the scenarios, he either first takes brown and then brown, or first takes black and then black. Okay? And so really take a second and look at those words there. See, we have and. Oops, it's not letting me. Whoops, maybe now it works. And or and. Okay, so now we're going to turn those words into math. Okay, so probably that he first takes brown is right here. See, so probably he first takes brown is going to be 3 out of 7. And is a multiply. And then another brown, which is here, is going to be 2 over 6. Or we're going to add first takes black which I will do it in, whatever, I'll go with pink. Okay, first takes black, and then another black, which is 3/6. Okay, so if I look at it that way, now it makes a lot more sense. Okay, so here in red, I will have 3/7 times 2/6. If I multiply straight across. So 3 times 2 is 6. 7 times 6 is 42. Okay, on the right side, I have 4 times 3, which is 12. Divided by 7 times 6 is 42. Okay, when you are adding, um, the only thing that matters is that the denominators are the same. So if the denominators are the same, this suddenly turns into 6 plus 12 divided by 42. Okay, the denominators do not add. They just need to be the same for you in order to be able to combine them, okay? So 6 plus 12 is 18 divided by 42, whatever that is, okay? That is 3/7, which is pretty much 0.429, which in decimal, or in parentheses, in percent, is 42.9%. Okay, any of those three options will give you the answer. See? Will give you full credit. So that is right there. Whoops, not what I intended to do. So that is right there for part B. All right? Either 3/7, 0.429, or 42.9%. How did I get that decimal? I just divided 3 by 7. There it is. 3 significant figures. Ta-da. Okay, that is part B. See? For part C, we need to find out that given, given that Carl has 2 socks of the same color, find the probability that he has 2 brown socks. All right, so the sort of cool thing about the given probability is that it do I have more space down here? Damn. All right, I can do it up here maybe. Yeah. So the cool thing about given is that it sort of restricts the bag where you're taking them from. See? So it makes like your area of possibilities much lower than before. Okay? Now, let's pull up our formula booklet. Let's look for a given probability, and it's not there. See? Another name they can put for it is conditional. So this conditional probability is the same as given. All right? It's important to get to know your formula booklet. This is basically given. Okay? So I'm going to go ahead and write that formula now. We have A vertical line B equals P A, this symbol B, divided by PB. Now, what does this mean in words? Okay, P line B is going to be probability of A given B. Okay, probability of A given B equals probability of A and B. Okay, and so that symbol here is for and. A way that I like to memorize it is that this N looks a little bit like that. So N and N is and. Okay, this dash here is for given. Okay, is getting divided by probability of B. Okay, so that is like putting these symbols into words. Okay, let me just highlight some more stuff. And then and. Okay, perfect. Yeah. All right, and now that we have it defined like this, we just kind of have to figure out what is A, what is B, but much more importantly, which is the key thing about conditional probability, is how did my universe of options get restricted? Okay, that is the biggest question you can do. All right, how do I leave this a little more clear? If you do a quick Venn diagram, okay, of your A and your B, for example, all right, you have these two big circles, and probability of A given B means that you're looking at the chance that you get A here in red. Whoa, how the hell did I just do that? All right, so sorry about that. Uh, probability of A given B is what is the chance that you roll here in red, given that you're picking here in blue? And so you're not like, for example, this is probability of A given B. See, you're picking from the blue, hoping that you get red, and so this is your universe is what's in yellow. See, you're picking from what's in yellow, hoping that you get red. Okay, which is much different than I say the probability of say A and B. Okay, which means that here in the same Venn diagram, okay, you are picking from everything and hoping that you get red. Okay? And so here is without conditional probability, here is with conditional probability. See? So the universe you're picking from, what I drew in yellow, gets restricted. Okay, so what am I restricting here? Well, here it says, given that Carl has two socks of the same color, okay, so A and B is going to be same color, find the probability that he has two brown socks. And so suddenly, we do not care about black socks. All of this part of my universe does not matter anymore. See, I am only focused on brown socks. So if I'm only focused on brown socks, that means I am going down through this line that's in red. See? So I would go ahead and put 3/7 times 2/6. And since I'm restricting my universe, down here is my restriction, okay? What is my restriction? That I have to go through the path on the top initially. I have to go through the path on the top, and the path on the top has a probability of 3/7. So if I have to go through the path on the top, I'm forgetting the path on the bottom. My restriction is that this has to be 3/7. And so that is, I know conditional probability is confusing, okay, but the key idea is how do my options get restricted? And so this goes away with this. I end up with, quite simply, 2/6, which is 1/3, which is the same as 0.333 or 33.3%. All right, yeah, that is part C. So, the key things for number 10 is understanding the tree diagram, the thing that these probabilities add up to 1, ¿cierto? Understanding when the denominator gets subtracted by one event to the next, and also that condition. Oh yeah, that and or is multiply or add respectively. Think in that language. And lastly, that conditional probability. The biggest thing you need to focus on is how it restricts your universe. I think this that I drew in yellow is a good example. See, for the example on the left, your normal one, you're picking from all of this box. In the right with conditional probability, you're picking only from this circle. It restricts where you pick from, basically, and that's why the denominator, which is like your total cases, is what gets played with. Ladies and gentlemen, that is for number 10. All right, now number 11. Okay, number 11, I'm just gonna be honest, it's a little fucked. Okay, it's hard. Yeah, so you're in for a ride. They tell us that the strength of earthquakes is measured on the Richter magnitude scale with values typically between 0 and 8, where 8 is the most severe. The Gutenberg-Richter equation gives the average number of earthquakes per year, n. Okay, so what is n? N is average number of earthquakes per year is n, which have a magnitude of at least m. So m is going to be magnitude. Okay, for a particular region, the equation is blah. So this here is my equation. For some a symbol, big R. All right, what the hell is that? So when they say a symbol, okay, that symbol means that a is part of the following sets of numbers. R is going to be all real numbers, okay? So all real numbers is going to be anything from negative infinity to positive infinity. Pretty much, okay? And it has to be divisible, a couple of other things. Yeah, but that's what it is, okay? The other things you can encounter is this weird symbol, which is like a very fancy Z that I don't think I even drew correctly, okay? Okay, that is for integers, see? Again, I'm just giving you context of what can show up. Integers is -1, 0, 1, 2. Okay, so whole numbers that include negatives. Natural numbers, which is just going to be like some fancy n, is going to be integers, but only the positive ones, okay? Alright, so that was just a quick lesson on what that means. So a has to be a real number, okay? So it can be 0.4, it can be stuff like that, alright? Yeah, let's see what happens. This region has an average of 100 earthquakes per year with a magnitude of at least 3, and we need to find the value of a. Alright, so the hard part here is really understanding what this formula is talking about, okay? Chances are most of you saw logs for just a little bit, okay? So if you ever face something like this in a test, whether it's a log or not, really think about the context and work with that, okay? So if they tell you that this region has an average of 100 earthquakes per year, or do I have a variable that talks about average earthquakes per year? Yes, I highlighted it. And this is why it's important to highlight your buzzwords. Average number of earthquakes per year is going to be n. Okay, so this here is telling me that n is 100. The magnitude of at least 3. Did I talk about magnitude at some point? Yes, right here, buzzword. So magnitude is 3. Okay, now we're getting somewhere. See, even if you don't know what log does, now we're getting somewhere. Dale? So for part A, find the value of A. Alright, so my equation is log 10 base 10 big N equals A minus big M. So if I go ahead and plug all of that in, see, I will have that log 10 with N 100 equals A minus 3. Okay, now I'm getting somewhere, see? Now this on the left, again, it's part of understanding how a log works and everything, is an actual number, okay, that you can find from your calculator. You can actually go log this number next to the 7, put 100, and there you go, it's 2. And now you might be thinking, okay, but this thing in your uh, calculator doesn't have the little 10. Okay, that's because the default is for there to be a 10 there, okay? That would be the base of the log. I don't want to get too much into logs because whatever, man. This isn't like a log problem, okay? It's just part of the equation. See? Plug in log 100. That is your thing on the left. This is 2. 2 equals a minus 3. Get a alone. Add 3 to both sides. A equals 5. Part A is that a equals 5. Okay, so then they tell us that the equation for this region can also be written as blah. N equals b divided by 10m. So, I already said that n is 100 and that m is 3. So let's figure that out. Okay, so n equals b divided by 10m to the power of m. So n is 100, which equals b divided by 10 to the power of 3. Okay, so even though this might look a little bit weird, you really gotta fall back on your principles of math. See? You wanna find b. You wanna get b alone. What is bothering b? B is being divided. It's being divided by 10 to the power of 3. So what do you do with 10 to the power of 3? You multiply by 10 to the power of 3. It's the inverse operation. What is bothering b? Something's being divided. What is the opposite of divide? You multiply. Okay, multiply by 10 over 3. Both sides. What does this do? Bada bim, bada boom. That goes away. I end up with b alone. B equals 10 to the power of 3 times 100. Alright, I can literally do that on my calculator. 10 to the power of 3 times 100 gives me a whole lot of zeros. 1, 2, 3, 4, 5. B equals 1, 2, 3, 4, 5. Is that right? 1, 2, 3, 4, 5. It does look right to me. That is B. Cool. Okay. Not that hard, eh? I knew you could do this. Part C. Given that given that m is greater than 0 but less than 8, find a range for n. Alright, this is where some people get like a little tripped up. See? So, range, okay, is going to be lowest and highest possible value. Thus the name range. And my equation or my formula goes from a certain amount to a certain amount. So m can only go from 0 to 8. Okay? Alright, now we're getting somewhere. So if I go ahead and pull out my y equals and graph, ¿cierto? I'm going to be graphing the thing in red. I found out that b was 1,000. Okay? Sorry, 100,000. How many zeros is that? 1, 2, 3, 4, 5. Divided by 10 to the power of m. I can go ahead and graph this. See? Alright, obviously the first time you graph it's probably not going to look that pretty. I'm going to try zoom standard or zoom fit. Zoom fit. Okay, it looks a little better, so I'm getting there. In fact, that might be good enough. And so this thing, this thing looks like this, okay? And so over here in blue is going to be my 0. At some point, I'm just going to call here, it's going to be my 8, okay? So that means my range is going to be whatever this value is up until this value here, okay? That's going to be my range. So let's try and find it out. All right, what I suggest you do is that from here, you can actually pull out your table. So you can do second table or second graph to hit table. And here you can go from 0 until 8 and see what values you get. Okay? So that actually allows me to find these 2 points here. This point here, according to this thing, when x is 8, when x is 8, y is 1 divided by 1,000. And when x is 0, okay, we have that y is probably a very big number. 1, 2, 3, 4, 5. 5 zeros. So 1, 1, 2, 3, 4, 5. It's that number. See, 100,000. Okay, so that would be my range. It would be from here to here. That is my range. Now, of course, you need to write it in a more fancy way. You can say that my range for n goes from this to this. Okay, and if you draw the graph, you're going to get full credit. The more fancy way that I'm sure some of you are asking for, so 1 divided by 1,000, which is this guy here, okay, 1 divided by 1,000 is going to give you 0.001. So my n goes from here. Wait, I'm having trouble putting the symbol I'm trying to put. Oh no. Oh, give me 1 second. Apologies. Ah, there we go. Okay. So my n goes from that 0.001 up until 100,000. So that is another way you can write your answer. Okay. So that would be for part C. All right, and now for part D, they tell us that the expected length of time in years between earthquakes with a magnitude of at least m is 1 over n. Okay. Within this region, the most severe earthquake recorded had a magnitude of 7.2. Magnitude 7.2. All right, keep talking. For part D, we need to find the expected length of time between this earthquake and the next earthquake of at least this magnitude. At least this magnitude. Give your answer to the nearest year. Okay, cool. Interesting. So there's a lot of talk about at least this, at least this, at least this what? At least this magnitude. And so which magnitude are we talking about? We're talking about 7.2. So m is going to be 7.2. All right, so that's my first hint. The second hint is that once I'm able to plug in 1 over n, I will find the expected length of time in years, okay? Which is basically part D, see? So once I'm able to find n, once I find this n, I'm good to go, see? And so, n equals what? What tools do I have at my disposal? Well, over here that I'm going to now put in brown is an n equals. So n equals b divided by 10 over m. Do I have b? I do. Do I have m? I also do. So what is my n in this case? I will do it. I don't really have space. I'm going to do it up here. All right. So what is my n value? N equals b divided by 10 to the power of m. From before, we identified that b is 100,000. We said that m is 7.2. And so this gives me an n value of, just trust me on this one, okay? Plug it into your calculator, you end up with 0.0063095. Okay, that is my n value, see? Now, we said that for the expected length of time in years between earthquakes with a magnitude of at least m is 1 over n, see? So I need to plug in 1 over n. We just found out what n was. So 1 over n is going to be 1 over this big number. I plug all of this into my calculator and I end up with 10 to the power of 2.2. See? Your calculator might spit it a little bit different, so let me just show you what shows up. I'm going to put a fraction, 1 divided by 0.0063095. It gave me 158.49. Okay? So again, you can plug this in again. It's going to give you the same number. I just wanted to show it because some calculators give it differently. But there it is. Okay, it's basically the same number. You're good to go. This is basically 158, 3 significant figures, which is 158 what? 158 years. So that is for part D. I think the hardest part for part D is being very organized on the fact that you're trying to find 1 over n. See? This exercise spits a lot of information at you, and there's certain things you can't lose track of. Okay? I know there's a lot of words when it says at least this magnitude, expected length of time, blah, blah, blah. Okay, go for the important stuff. See? You read magnitude, you highlight magnitude. Where else does magnitude show up? Here, magnitude 7.2. Boom, m is 7.2. You work from there. You need to find n. What is n? Have I used n before? Here's a formula for n. Okay, that's the sort of thing you have to go for. Even if you don't know shit about logs, if you're organized in your approach and you think about what you need, what you have, and all that kind of stuff, that is how you can go through these problems. All right? So that is for number 11. All right, and now for number 12, we have that a company's profit per year was found to be changing at a rate of blah. Where P, okay, P is company's profit in thousands of dollars, and T is time. Which time? Time since the company was founded. Okay, all of this, units, years. Part A, determine whether the profit, okay, profit, is increasing or decreasing when T equals 2. Okay, cool. Let's figure it out. So, first things first, when you have dP over dt, or you might encounter stuff like, I don't know, derivative of f, derivative of x, might be written with that fancy symbol. This is all rate of change. Okay, the moment you go from f of x to the derivative of f of x, or also, which is a synonym, this down here, okay, this is all now rate of change, okay? And so when you plug in, say, x equals 5 in this scenario, you're saying, what is my rate of change at x equals 5? Ah, okay. So now that we understand that idea, if over here it asks, yo, is the profit increasing or decreasing when t equals 2? So when the company is 2 years old, is it increasing or decreasing? Have it got it figured it? Did they figure it out already or not? You gotta take this dp over dt and plug in t equals 2. Okay? So plug in t equals 2. So 3 parentheses 2 squared minus 8 parentheses 2. You end up with 3 times 4 because of 2 squared minus 16 because of 8 times 2. This is 12 minus 16, which gives you negative 4. Okay, so what is my rate of change when t equals 2? My rate of change when t equals 2 is negative 4. Is that positive or negative? It's negative. So you can say that p is decreasing. And what is your argument? There's a couple ways you can put it. The one that I like the most is just saying p is decreasing because negative 4 is less than 0. See? Or you can say because dp over dt equals negative 4. Yeah, this is probably your safer bet. All right, but point is, it's a negative, so then it has to be decreasing. Period. That is for part A. Then they tell us that 1 year after the company was founded, the profit was $4,000. God dang, bruh. Part B. Find an expression for PT when t is greater than or equal to 0. So, notice, here we have the derivative of p in respects to t. Okay, if you want to go back to just pt, you have to do the integral. Okay, what do I mean by this? If I have pt, I want to go to dp over dt, I have to do the derivative. If I want to go back from dp over dt up here, I need to do the integral. All right, cool. So once I do the integral, I can get back up there and I'm good to go. See? All right, interesting. So the integral is, as you can see, the opposite of the derivative. Okay, they are inverse operations. All right. So however you do the derivative here, you do it backwards to find the integral. And so here I only have exponents. See? Right here. So that means I just need to do basically the derivative of an exponent but backwards. All right. So I know that's a little bit weird, but hang on with me. All right. I'm going to give you an example first. Okay. If I have x squared and I ask you to do the derivative of this, you will take that 2, pop it in front, multiplying, and do minus 1. What do you end up with? You end up with 2x to the power of 1, which is just 2x. And now, if I ask you to go backwards from here, okay, if I ask you to go backwards from here, because this 2 is down in front, you immediately know that you have x squared, okay? And that's sort of like a big hint, okay, for how to do the integral. See? All right, and now for part B, they tell us that 1 year after the company was founded, the profit was $4,000. The damn. We need to find an expression for PT when t is greater than or equal to 0. Okay. So as I mentioned earlier, we need to do the opposite of a derivative. See? So what I have right now is 3t squared minus 8t. And so I need to do the integral of this. See, I need to think backwards basically. All right. So if I think initially about how these numbers were when they got derivatived, okay? For example, here, see, because there is a surviving t to the power of 1, that means this used to be to the power of 2, okay? I know that for a fact, so there has to be a t to the power of 2. If here there's a t squared, that means there used to be a t to the power of 3, okay? That is the first thing I'm going to start off by doing, right? And now I can kind of think about the multiplying and dividing that happens when I pull this 2 in front, see? So if I pull this in front and ended up with a 3, that means that up here there was just a 1. Why? Because I would be doing 3 times 1. All right, so here, the one on the left is Gucci. The one on the right is a little bit different. So I need to think that once I did the derivative, okay, and pulled it down in front, I ended up with 8t. See? So I had 2 times something gave me 8. 2 times something gives me 8. That something has to be 4. And so over here, I'm just going to go ahead and put 4. And so this would be the sort of PT I'm going for. See? PT equals this. Now, notice, in my approach I said, okay, this guy survived, ¿cierto? It survived after the derivative because there's a t squared. That means it used to be a t cubed, at least. This guy also survived, so it had to be a t squared, at least. Okay, what about t to the power of 1? Or something without t? What happens there? So anything to the power of 1, okay, would have been like a constant, see? But anything without t, I'm not really accounting it for, see? So that is a constant that would simply disappear. What do I mean by this? If you have f of x equals x squared plus 2x plus 3, and you do the derivative of this, okay, you end up with 2x plus 2, and this 3 disappears, ¿cierto? Straight up disappears. Consider doing the integral from here, see? If you do the integral from here, you would say, all right, so because I have x to the power of 1, that means there used to be an x squared. If I have a 2 that survived, that means there has to be an x to the power of 1, ¿cierto? And you would end up concluding that it's 2x squared plus 2x. But you would be leaving aside this plus 3. And so what you do when you do an integral, always, always, do not forget, is that you put plus c. Because this symbolizes any 3 that you might be missing, any constant that you might be missing. So right now, my current scenario is this right here that I'm putting in purple. P of t equals t cubed minus 4t squared plus c. And so until I find the value of c, I'm not done yet, see? All right, so right now I have 3 sort of variables going on. I have P of t, I have t, and I have c. Okay, those are my 3 variables, all right? So, what is P of t? P of t is profit. What is t? T is time. What is c? C is constant. All right, so can I plug 2 of these right away and find my constant? Yes, you can, which is actually something kind of cool about these integral problems. They do follow a pattern, okay? You usually have to find that last constant, and they give you the information for it. So, 1 year after the company was founded, the profit was $4,000. Notice what I highlighted. 1 year, year is time, t equals 1. Profit, 4,000, p equals 4. What is my set of points? 1, comma, 4. Interesting. So I go ahead and plug in 1, comma 4 down here. Whoops. If I take this 1, comma 4 and plug it in down here, this guy in purple, I end up with 4 equals 1 cubed minus 4 times 1 squared plus c. So 4 equals 1 times 1 times 1 is 1 minus 4 times 1 plus c. That tells me that we have 4 equals c minus 3, which means that c equals 7. So now that I found that c equals 7, I'm plugging it back to my thing in purple. And my last thing that I'm going to do is that P of t equals t cubed minus 4t squared plus c. We said that c was 7. This is for part B. And that is for number 12. I think the hardest part is really understanding that the integral is the opposite of derivative. And once you practice a few of those, you really understand that it's not that hard. My biggest tip that I can give is really focus on the exponents, okay? Work around the exponents. Think about what has to happen before and after they get derivative. That is for number 12. All right, and for the last one, number 13, we have that a ball is dropped from a height of 1.8 meters and bounces on the ground. The maximum height reached by the ball after each bounce is 85% of the previous maximum height. All right, so let's add a little bit of perspective to this. So 1.8 meters, see, is the first one, which is over here. So 0, comma 1.8 meters. And the following ones are 85% of the previous maximum height. So this one, okay, because it's 85% less than the last one, ¿cierto? Is basically there's a decrease of 15% here. See? There's another decrease of 15% with the last one, and so on and so forth, okay? So that is what it means by the 85%. All right, for part A, we need to show that the maximum height reached by the ball after it has bounced for the sixth time is 68 centimeters to the nearest centimeter. All right, so here, I think the tough part is actually identifying what type of problem it is, okay? And so because we have an initial bounce, the first one, second, third, fourth, etc., you can kind of look at it as a sequence, see? And so this is a sequence that is decreasing by a certain amount. Now, in which nature is it decreasing? It is decreasing in a percent, okay? So it is not decreasing by a flat value. We're not saying that each time it's minus 3. We're saying that it is minus 15% in respects to the last one. Okay, so it's not it might start with minus 3, but then it's going to be minus 2, then it's going to be minus 1.5, stuff like that. See? And so because it is not decreasing in a linear fashion, we have a geometric sequence. And so let's talk about that first. See, so I'm going to pull up my formula booklet. I'm going to go ahead and look for sequence. And here we have arithmetic up top, arithmetic, geometric. And so arithmetic is going to be adding or subtracting. Geometric is going to be multiplying or dividing, okay? Because we're talking about a percent, 85%, this is the same as 0.85. And it affects each term individually. It's not gradual. It's going to be a geometric sequence, okay? So these are the formulas that I can play around with, and we can work from there, all right? So for part A, we need to show that the maximum height reached by the ball after it has bounced for the sixth time, okay, is 68 centimeters to the nearest centimeter. All right, interesting. So, the nth term of a geometric sequence, the one up top, asks for un, which equals u1 r to the power of n minus 1. All right, so because we're talking about the sixth time, that is a big hint that n has to equal 6. So I'm going to go ahead and put that. So we have u6 equals u1 times r to the power of 6 minus 1. All right, what else can I fill in? Well, this r, what is this r? R accounts for rate of change. If you notice, here I have r. For geometric sequences, I have a bunch of r's. And for arithmetic sequence, I have a bunch of d's. D's nuts. A bunch of d's for difference. Okay? D for difference. All right? R for rate of change, D for difference, arithmetic, geometric, blah, blah, blah. See? So what is my rate of change here? Well, I know that it decreases by 15%. And so I'm going to go ahead and say that R is 0.85. Since it is 85% from the last bounce, decreases by 15%. 100 minus 15% gives you that 85. Okay? Cool. So I'm going to have that U6 equals U1 times 0.85 to the power of 6 minus 1. And last but not least, I need to find what the heck U1 is. See? So, this here technically would be sort of like my U0. See? After the first bounce, I'm going to have my U1, then I have my U2, then I have my U3. All right, cool. So how can I find U1? Well, U1 is simply going to be applying this 85% once. To what do I apply it? To U0. At what height is it? At 1.8. So I'm going to take this 1.8, apply like the rate of change only once, and this right here is going to be U1. See? I could technically do this 5 more times and get my answer, but I'd rather figure out what u1 is right away for purposes of the problem, okay? But u1, as we just found out, is going to be this 1.8 times the rate of change only once. u1 is going to be 1.53. All right, so now I can solve it. So u6 equals u1, which is 1.53, times 0.85 to the power of 6 minus 1. You put all of that into your calculator. U6 is going to give you, let's find out actually. Let's find out. So it's going to give me 1.53 parentheses 0.85 to the power of 6 minus 1. It gives me that number. See, so it's going to give me 0.6788. Now, because I need to round it to the nearest centimeter, okay, that means I will be picking on, wait, actually, it gave me a decimal. Yo, that's weird. All right, give me a second. All right, perfect. So this right here, okay, I know it looks a little bit weird, but because it's in decimal, okay, this is actually a meter. So this is 0.67 meters. All right, how do I know that? I know that because this 1.8 is in meters, okay? So that means that since I'm working with meters, this is 0.67 meters. And if I turn that into centimeters, right, I have 100 centimeters in 1 meter. So that means that this U6 is actually 67.88 centimeters. And since I'm rounding to the nearest centimeter, the nearest centimeter is going to be comparing this guy with this guy. Do I round it up or down? I round it up because it's above 5. So U6 is going to be 68. U6 is going to be 68. 68 what? 68 centimeters. So that is for part A. Okay, and now for part B, we need to find the number of times after the first bounce that the maximum height reached is greater than 10 centimeters. All right, cool. So what we need to understand here is the following. 10 centimeters, because this is in meters, okay? 10 centimeters is going to be, I don't know, like 0.1, yeah? And at some point with some of these bounces, at some point it's not going to cross 0.1 anymore, okay? And so I can actually set it up with math language in the following way. I can say I need to find anything that is greater than 0.1. Right, so this is how I'm going to start. It has to be greater than 0.1. And what goes here? Well, here goes whichever term breaks that pattern. See? So let's say after this pattern, after this guy here, the rest of them is less than 0.10. And so from here to the left are all the ones I need to count. So this is the guy we're about to discover, right? And how do I express this guy here? Well, we have our equation down here. This guy there. This guy here, okay? What is that asking for? Well, is the nth term of a geometric sequence. So that would allow us to find that specific term if we just leave n as a variable, see? So we don't know what n this is, but we know that it needs to be greater than 0.1, see? So what is that n? Well, I can just go ahead and plug it in. So I have u1 times r to the power of n minus 1. I already know u1, ¿cierto? We said that u1 was 1.53 from back here. So we can have 1.53 times r. R we said was 0.85, okay, to the power of n minus 1. And if I find the value of n, I'm going to be finding this guy here, and I can work from there. All right? Okay, there's a couple of ways to approach this. And I know some of you are thinking, damn, I have an exponent. I mean, I have a variable in my exponent. That shit's fucked. See? So what we can do to solve that, or my favorite trick, is calc intersect. See? So you're going to call this y1, call this y2, do calc intersect, And that helps you play around the fact that you have a variable on your exponents. See? So you will be basically asking your calculator what makes this true. So if I put 0.1 here, on the other side I find 1.53 times 0.85 to the power of n minus 1, and I graph it and find the intersect, I will find my key point. See? If you're a little bit confused with the calc intersect, I do have a video on it, but the intuition that I can share with you now is that wherever these two lines intersect is what makes it sort of like true, okay? And so that's going to be my key point, and with context I can figure it out. All right, so here I see one of my lines. I do not see 0.1. Got to play around with my window a little bit until it shows up. Gonna go ahead and put y max is 1, y minimum is 0, and I think it might show up now actually. I'm probably gonna make a bigger x. I'll put like 25. Play from there. Yeah, that is actually a pretty good graph. So now if I do calc intersect, I can work from there. See? All right, it gives me 17.78. So that means that in my term number 17.78 and onwards, it is not greater than 10. So that means that my term 17 and back is greater than 10. Perfect. So if I literally write calc intersect, yes, you can do this in your test and get full credit. You can say that you got 17.7, 7.78, and that means that for part B, it happens 17 times. In fact, you can pretty much write that n had to be 17.8 or 17.78, and you are good to go. See? All right, and now for part C, probably the hardest one. See, we need to find the total vertical distance traveled by the ball from the point at which it is dropped until the fourth bounce. All right, so let me just make some space because we are going to need it. Now let's really dig into like the heart of this problem. Okay, so on one side, okay, you have your terms that you plug in, so u0, u1, etc. And then you have like what each term represents. See? So what the term represents is the total height. See? It's always going to give you the maximum height after that bounce. Okay? And so what I can actually do is use the following formula. I can use the formula over here for sum of n terms of a finite geometric sequence. And so let's take a second and see that I have two equations. I can either use the one on the left or the one on the right. The one on the left, what does it ask for? It asks for u1, it asks for r, it asks for n. The one on the right asks for u1, asks for r, asks for n. So I can use either, okay? It doesn't matter. Now, why is it worth asking yourself what do you need? Because whenever you use the arithmetic one, it does matter, see? For the one on the left, you need n, you need u1, you need n, you need d, okay? I marked n twice, my bad. And on the right side, you need n, you need u1, and you need un. Okay, you do not need d for the one on the right. So there is a difference here. There isn't a difference on the bottom. So whatever. I'm going to use this one here. All right. Oops, I'm going to use the one on the right, I mean. ¿Vale? So, because I am now analyzing from the point at which it is dropped, okay, my u1, in a way, is going to be this 1.8. See? So bear with me for a sec. It'll make sense in a second. I'm going to go ahead and put that my u1 for now is 1.8. See? Again, context matters because we're doing it from the point at which it's dropped. My u1 is now 1.8. See? u1 is 1.8. R is still going to be 0.85. And since we're going until the fourth bounce, n has to be 4. So we pull up my equation. It looks something like this. S of n equals u1 parentheses, 1 minus r to the power of n, parentheses close, denominator 1 minus r. All of this with r not being equal to 1. Okay, so if I go ahead and start plugging in, I'm first going to plug in that n is 4. So S4 equals u1, 1 minus r to the power of n, and n is 4. This is an r, divided by 1 minus r. All right, let's go ahead and plug in u1 now. We said that u1 was 1.8, so I'm going to put 1.8 over here. Let's go ahead and plug in r, which you said was 0.85. So here it is, and 0.85. All right, cool. So if I plug all of this into my calculator, I end up with 5.735 925. Now, this is the sum of all of my terms. See? Now, here's something kind of weird, okay? These terms are basically adding this height. See? They are adding this height. But what we need to understand, okay, what we need to understand is that that height is traveled twice. Because we're talking about vertical distance, okay, that height is covered here and it is covered here. Both of those are vertical distance, okay? Both of these are vertical distance. So right now, what my sum formula did is that it added this, well, technically, it added this, 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 and this. It added all of those. And so from one side, I actually need to subtract this guy, which is how much? 1.8. So I'm going to go ahead and take that guy and subtract 1.8 from it. And I also need to understand that because all of these distances are covered twice, first in blue, then in red, see? It means I have to multiply by 2. So if I multiply by 2 and also subtract 1.8, I end up with 9.67185. Don't forget your units meters. Significant figures, 9.67 meters. And that would be for part C. Probably the weirdest one. I think the context matters a lot there. See? Take a minute, really try to absorb it. Have clear why you subtracted 1.8. I'm just going to explain it one more time. This 1.8 gets deleted because the sum formula is adding this guy here. So you have to subtract it. It's 1.8. You have to subtract it. And you have to multiply by 2 because the sum formula is only adding this height here. See? When in fact you need to add when it goes up, when it goes down, when it goes up, when it goes down. If you use it only once, you're adding only if it goes up. Or only if it goes down. But you need both. So, that actually concludes this paper. That is for number 13. And yeah, I hope it helped.